chapter 7 and chapter 8 or chapter 7, just depending on what we get through. We're still doing pretty good.
I really hope you're supposed to read it. Because I have some classes.
I care more about you guys getting it than the deadline. The deadline is still important, and you can't be on like chapter 3 to the end of the semester. Like there's simply no way. Every once in a while, somebody, I don't know, most of my students do well in stats. I do have people fail once in a while, but usually they just like do half the work and then they're all confused. Like, well, Blackboard said I got an A. It's like, well, Blackboard lies. Like, I don't really expect you guys to read the stats book. I would use it more as a reference because it's stats and it's probably about as much fun as watching paint dry reading it. Like, if we're being honest here, like Gen Psych or a different course, it's probably fun to read about, but stats, most of them aren't written that great. So like you should totally have the book and it doesn't hurt to read, but hopefully between all the other activities we have and the lectures and everything, you guys are as becoming much clearer to you versus the book. Because if you just read the book on your own, it's like foundational, I would say at best. I don't think it's gonna just all click because they're writing about math and they're not all that creative. So I think we went as far as like pre-test for chapter 7. At this point, I think everything through chapter 6 for the post-test. If you attempted it, I gave you all the points on pre-tests. So what? Yeah. Just let me call in, Carlos. I'm thinking about electric car. I don't know if it'll be I'm thinking Toyota because they have a SUV coming out into 2023. It goes 250 miles up to charge, and it has like the 110, the double charge, and the triple fast charge. Because I did the math, and that's what 42. Really? 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 Okay. But I want either front wheel drive or all wheel drive, preferably all wheel drive because of the snow. My wife's not a good driver. No, I'll tell you why in a moment.
Yeah. I got my car like, so that was perfect time because it was right before everything started going.
Oh, maybe that's worth it. But part of our research before buying the Toyota is to compare them against Tesla. So if there's used Teslas that are going to have a good long battery life, that might be worth it. Especially the auto driving mode, that'd be even cooler. I just think she's from Venezuela, so she like she had a federal job, so there's a lot more corruption with their government than ours. So she had a driver's license, but she drove like grandma, and I couldn't figure out why. She didn't have a driver's test. They just gave her a license, because of the job she had, because she was like worked for the Federal Ministry of Education or something. So I can drive like with rear-wheel drive in like a blizzard, it's fine, but good morning. So it's the quick attendance. It's just like I said, not tied to points or anything. It's just they like to know primarily for financial aid here. So here. Oh, okay. Let's go like this. Seven. Everybody ready? So we'll walk through chapter 7. Then we'll do some worksheets, activities. If we have time, we'll do chapter 8. I don't think we're going to do more than 2 chapters today at best, or we'll just do chapter 7 depending on questions, etc. So, hey, come on. Here. Everybody, a moment. So we'll just start with something funny anecdotally. I have a friend in Wisconsin since like high school, and I lived in California for several years. When I missed my flight once, I think she's a little crazy. I told her this to her face. She's a friend for a long time. Well, she decided that I was still going to be going to the bar with her, even though I missed my flight. She did a life-size cardboard cutout and took it to the bar and then posted it all over Facebook. And then for years, her group of friends that were new thought that I wasn't real. So whenever I see them now, I mess with them. The first time I actually met like some like the mutual friends, like a buddy of mine is married to a friend of hers, and his wife was like, yeah, he's not real. He's in your mind because, you know, like the Facebook thing and everything. So the first time I met him, I met like the other group of people that had joined the group of friends. She like asked for my ID. So to this day, like whenever I see them, I'm always like, I'm Jason Mack, or am I? Just to like mess with her. So she made it. And she took a picture off Facebook and she printed out like a regular face size copy with a color printer. Yeah. And then went like all over the place. They're like, yeah, that's just a cardboard cutout. He's not real. So let's try to lighten the mood a little bit before we jump into math. So probability, sampling distributions. We're going to walk through all these things today. Inferential, obviously, meaning there's going to be some review. We'll talk about standard error. And then transformations. Hello. This is the funny story. Just now. But what you missed is that I have a friend from high school that I missed my plane once. So she decided that I was still going to go to the bar. So she took and made a life-size cardboard cutout and took it to the bar, posted all over Facebook. And now like some of like the friends that like a buddy of mine that's also her friend is like, his wife was like, yeah, he's not real. So the first time I met her, she's like asking for like ID. So now to this day, whenever I hang out with them in Wisconsin, I'm always like, I'm Jason Mack, or am I? Just to like mess with them. And then she says stuff like, oh, thanks for posing as him. I'll make sure to send you that check in front of him all the time just to mess with them. So that's always fun. So we'll go through this stuff today. So inferential statistics, inferring, that's like you're looking for meaning. Measure mean, variance, again, mean, average, variance, scores varying to gain value, and the variance in the population. It's just how the scores really differ. In fact, I should probably, while you're taking notes there. Bring that up on this side so that the recording makes sense for everybody. So let me just go ahead and do the dual screens here, and then we'll go on to the next thing. Everybody just walked in, it's chapter 7 and or 8, depending on what we get through today. So resources. Chapter 7. If that opens. Okay. So how would you understand your score on an exam? You would generalize it to the population. We're trying to infer. We're trying to see how you did. So you ask a question, for example, how good is your score compared to the mean? Identify individuals of interest, like other students. Also, just take the exam in the class, select a proportion, and then you relate the scores to it. And then you can determine how well you did. So if like you compared it to the mean or the average, did you score with everybody? Great. If did you score above or below the average, then that's report that it would basically give you a sense to like interpret your score. Like, what does that actually mean in relation to how everybody else did? If you only have like 1 or 2 attempts and everything, or just 1 attempt, I probably would grade like that. Usually that has to do with like grading on a curve, like how did you compare to everybody else? But because we have all these attempts, it's based on the scores that you get. So then we infer, we try to figure out what happened in terms of the average or the mean to the population. Is that making sense so far? Some of this is a review, but we'll jump into more stuff. So you want random selection so that you don't have any error. So you want to be careful because you don't want to establish a pattern with random selection. If I said, okay, I'm going to talk to we have 2, 4, 6. So I'm going to talk to every second person. Okay, that's great. I end up with maybe 2 women, 1 guy. That's kind of good. I might say, well, that's not as representative, but maybe because there's only 50% of you. But the problem with random selection is if I start doing a pattern too much, it's no longer random. Like you don't want to always select like every 50th person. You want to be careful whatever your pattern is so that you don't end up having a bias. So you have the same probability of selecting each participant. So sample distributions, distribution of all possible sample means. So the sample means on the x-axis and the frequencies on the y-axis. So x is like the value and y would be like the number of times the thing happened, and then where they intersect is what that would look like. And then the hypothetical population, the mean and the variance. We'll do some hypothetical stuff today too. Or mean is average, variance, how much scores vary. You have to have at least 2 scores or they can't vary because it starts with the second score. That's where we get stuff like degrees of freedom, which is always n-1, because we were accounting for that one and we're also accounting for the sample. Obviously, when it's population, we don't deal with n-1, and that's to account for, as you remember, where it basically mimics the mean, depending on your margin of error on your sample or your population. So we have sample without replacement, most common method. For example, we're going to draw squares or triangles or something. Probably selecting the triangle or square. 88 squares, 2 have A, 2 have B, 2 have C, 2 have D. It'd be 2 out of 8. Because obviously there's 2 squares, that's your numerator, total sample size, your denominator 8. Second draw, if we don't replace the square, we have to account for the numerator and the denominator, so it's 1 out of 7 because we took away 1 out of all the probabilities. Does that all make sense to everybody. So then it changes it because we didn't replace it. So we have that so far. So then we have with replacement. So then if you replace it, it's usually not necessary because the populations are large. Morning. Probability of 100 women versus P is equal to 1/100. Selecting a second woman without replacement is 1/99. So it just depends if we're replacing or not. Like I said, it's not usually when you're doing research, you can use stuff like GPower. It's a free software program that tells you your probability in your test to make sure that it's like representative of the sample. There's other statistical stuff out there. GPower is really great. But usually it's 20 or 30 participants per variable if you're wondering, in terms of how you make sure your population is big enough. That's just like a general rule. It's still going to vary based on your statistical test, but generally speaking, about 20 or 30 per variable, more like 30 usually. So we're going to have this so far. This is in chapter 7, by the way, too. So if you're selecting a sample, you have to address a couple questions in terms of how they're selecting their samples. You want to be aware of like the context of it. Does order matter? In terms of how you select? Like I was mentioning, we want to be careful not to have too much of a pattern. We wouldn't want to select every 2 people because then we're always selecting every 2 people. Sampling with or without replacement. With replacement, your numerator and denominator are not affected. Without replacement, they are, because you have a smaller sample space and a smaller frequency of the thing happening. 2 strategies: you got to do theoretical sampling or experimental sampling. All right, so this is what that looks like visually with theoretical sampling. So, example, with theoretical sampling, we would take and we would look at all of these for your population. So an example, all possible samples of n is of size 2, n is equal to 2 are taken from this population of n equals 4. If you see the theoretical sampling, it allows for the most probable samples, which is 16, whereas the experimental allows for the fewest possible samples right here. You see those are crossed out. So that's the nuance between your theoretical and your experimental sampling, like everybody, or are we going like most possible outcomes or least possible outcomes? So that makes sense. We're going to walk through the math on how to do this. This is just more conceptual. Well, so the formula is n, large N to the small n power. Now I'm going to walk you through what that means step by step on worksheets in terms of your theoretical sampling formula. We'll probably do that like in like 10 or 15 minutes approximately or so. This is in chapter 7, so which is under like in Blackboard. And I'm recording and posting this on YouTube and on in the classroom. So like if you came in late, it's not like you're gonna miss really anything, but you did miss the story. So see, I can't tell you because you are still coming in. I'm gonna have to wait like you get 30 minutes now. But I'll recant it again, or in groups will tell you about it. So because I told it like twice, and then like more people came in. But don't worry, you'll hear it before the end of the class today. Actually, you know what? I'm gonna just mark you guys here real quick. Okay, you're here, perfect. And then over here. And we'll make sure that you're here alone because you're at the end. Present. Okay, cool. So theoretical sampling, order matters in sampling with replacement. Formula to determine is n to the n power. Don't worry, we're going to walk through this on worksheets in terms of what that means and how you get there. And everybody that's here did see the probability card trick, right? Just to know, everybody saw that? Not everybody. Okay, just curious. Okay. What was that? Okay. So n to n3 squared is equal to 9 samples. So 3 people, which is n sample of 2 participants, n is equal to 2, 9 possible samples. Anybody ever play like, what is it, Crimes Against Humanity or any of those, like, or Clue or any of those games where like it always ends a different way? It has to do with this formula and the amount of outcomes you can get. And usually you get into some pretty big numbers pretty quickly. So you could actually, if you wanted to, have a sense of how many different outcomes on those like Crimes Against Humanity card games, etc. That's why it never ends the same. So order does not matter in sample without replacement. This is most commonly used in behavioral research. Here is our formula and exclamation point. Don't worry, we have worksheets coming up where I literally give you a scenario and tell you how to plug this in. So just for now, just to know what the formula is, divided by small n, exclamation point, times capital N minus n, exclamation point. Don't worry if that doesn't make sense yet. We have worksheets with practical examples coming up, and I'll walk you through a couple of them. Right now, I would say just know what the formula is so you can plug it in. Because basically what will happen is I'll say out of this, what are the number of outcomes? And then I'll show you, like I said, step by step how to calculate that and that. And I'll show you on the slides in a moment when everybody has up to that point. Should be writing. So for example, experiment sampling, determine the number of samples of any size, select from the population. Population is 3 people, n is 3 samples possible, 2 participants in terms of who we're going to select out of the population. So n, exclamation point, is 3. 3 is our population. Samples possible are 2 participants. Small n is equal to 2. Select as many samples of 2 participants as possible from the population of 3. So we're going to say we want to get 2 people out of this total population. Now this makes sense if you just think about it, because we can't select more than 2 people out of 3 people if we're doing sets of 2. So our numerator is going to be 3 exclamation point, which is 3 times 2 times 1. So it's always the largest number, your population times 2 times 1, or 9 times 8 times 7 times 6, or whatever it is, all the way down. That's what that exclamation point means. And then 2, that's for small n, the number of groups of 2, times 3, which is your n, minus 2. So it's 2 times 1 on the outside of that parentheses to the left. And then 3 minus 2 is 1. So that's where we get 2 times 1 times 1. And we're going to walk through some worksheets where we're going to practice this too, with some specific scenarios. So it's not just random formulas here. Okay. Does that make sense so far to everybody? Just conceptually, like I said, we're going to do some practical examples in a moment. Yes.
So what is the explanation?
You multiply it by it. Basically, you take it, the number you're working with, and you take it times every number below it all the way down to 1. And then with this right here, you take whatever this is all the way down to 1. So because it's just 1, it's 1 times 1 in that spot. Did I answer that okay? Okay. So how well sampling mean estimates the population, construct sampling distribution 3 ways. We can do the unbiased estimator, the central limit theorem, or the minimum variance. So because the sample is a broad generalization of the population, we're trying to estimate it or guess. And then the ways we would do that would be your unbiased estimator, central limit theorem, and minimum variance. In terms of just sort of how we get that inferential meaning. So, well, you're all cut up, no problem. So for unbiased estimator, random accepted sample equals the value of the population parameter on average. So it's not an over or underestimate. We use the mean and the variance. So the rule is sample mean is an unbiased estimator of the population mean. Does everyone remember SE, or do you want to see that visually, what I just said? Does that help? Okay. So let me share both screens so that that works. And you can follow along if you go into, I'll show you where I'm going here, under announcements, and I'll do it on the other screen in a second. And then scroll down until you see, should be SE, dances the new statistics. Should look something kind of like this. If you go up to announcements, let's make sure we're sharing the screen here. And scroll down, you should have SE like that. So we have right here, this is going to be our mean, and this would be our error. So the smaller the error is, the closer it's going to be to the actual population mean. The larger this is, it's still going to be along these lines, but it's going to be further away from the population. So if I do take sample, do you see all the green right there? So we're inferring the population average from the sample. If I have a smaller error, if I take this, I do take sample, you see it's much closer. And same thing over here. If I take sample here with like 20, it's really close. I increase that, take sample, it's going to be further, it's going to be more variance, so to speak. It's going to be further away. So in terms of just like a visual and an unbiased estimator, hopefully that's helpful. Making sense, everybody, conceptually? Cool. All right, so we'll stop that. We'll go back to PowerPoint here, unbiased estimator. Sure. Okay, and slideshow, current slide. So the mean is equal to the sum of the X values divided by N, or the mean is equal to the mean on average. So the large mean is your sample mean, that Greek mu letter that looks like a U basically, that like in cursive, that is your population mean. So generally, just like I was showing you just now visually, they tend to be pretty close to each other. That's why we're allowed to infer. That's why it's usually about 30 people per variable. at least 20 on average for whatever you're doing. Like I was mentioning earlier, G-Power would tell you it's a free software program. It can tell you if you're trying to do a study what you actually need. You might not use that now, but you might use that at your job 5 years from now or a year from now. You never know when stats might be something that you're responsible for. It certainly happened for me. I was in charge of tracking our production using statistics, but I had a not so understanding manager of math. So he said a lot of crazy stuff about like macro and micro, which didn't make any sense at all. I don't know if it's because he had a master's in history or what his deal was, but just he didn't get math. Nothing's anything wrong with history, just this guy was kind of out there. So unbiased estimator. Suppose we select a sample size of 2 from the population of 3 with scores of 2, 5, and 8. Our mean is 5. Remember, the rule is a sample mean unbiased estimator. When the mean is equal to the sum of, remember, sigma is that Q for sum of X are your values divided by N on average. So we did that. So right here, we have our 9 samples on our left-hand column here. And then we take the mean. So the sample mean for each of these is this. So what we're doing is we're taking this, and we're getting a sample mean, the sum of X over N. So that and that divided by 2, 8, and so on. Then we sum all those together. The sum of all the means is 45. And we had a total of 9 samples, even though there were 2 in each sample. And then we do that to get our unbiased estimator, 45 over 9. Does that make sense? Does seeing it help? Yeah. And divided by 2 because there's 2 in your N. So I'm saying these two. Yeah, so we have, so we're doing sets of 2 of samples, but there's 9 samples total. So we're getting the mean of each individual sample, and then we're summing them all together. And then we're taking that divided by all the samples to get that mean. Like you could, I'm pretty sure you could add them all together without doing that, and it would still come out the same. Yeah, Katie. So 8 plus, so I need a marker. Let's walk through that. So we have A and A, which happens to be 8 and 8. So that our sample mean is 8. Now, how did we get there? Well, we took these, which is basically the sum of X over the N, which is going to be 2. So 16 divided by 2 is 8. And then we're doing that throughout. So if I just pick a random one, what? C and B, 2 and 5, 3.5. So it should be the same thing. So 7 divided by 2, yeah, that's 3.5.
Yeah, I was asking, like, is it like, you know how B is 5, like the letters, they just tell us that?
Yes. Yeah, they're saying substitute, but they tell you. And I'm going to tell you what we're looking at in the worksheets too. Question. So we have the central limit theorem. Shape of the sample distribution, sample means tends towards normal distribution. When I say normal distribution, I'm talking about the bell curve. Nothing skewed. We're saying that the shape of the sample distribution means is usually going to be symmetrical bell curve, regardless of the shape of the distribution. So it tends towards that bell curve, even if it is skewed. Probably distribution for obtaining the sample mean from the population is normal. So the empirical rule, 95% of all sample means in the population are within 2 standard deviations of the mean. Some of that is review. We talk about so this is intelligence scores. These are the standard deviations are usually about 15. Everybody's usually around here because that's your average. Some are above and below. But the 2 standard deviations to the left and right of the mean would be right here. Most everybody is between a 70 and a 130. Dude, there's smart people over here that are 145, 160, if it's even a true measure of intelligence. And there are definitely people that are over here 50, 55, 40, etc. But the two standard deviations, one standard deviation, two standard deviations, same thing, standard deviation, standard deviation. So 95% of the scores, most people are going to fall right here. So that's talking about. Make sense, everybody? Normal distribution. And then, of course, that represents what you can and cannot do cognitively processing, that sort of thing, under like the traditional intelligence model. You missed the funny story, but I'll make sure you hear about that before the day's out and tell everybody who's walking in late. So this is in chapter 7, by the way, if you're following along, and no worries, I'm recording. So regardless of the distribution of scores in the population, the distribution will be approximately normally distributed. Again, approximately, that's that bell curve, generally going to be symmetrical. At least 95% of possible means fall within standard deviations of the mean. Again, just really mimicking, the sample is going to mimic the population typically. This is all making sense so far, everybody. Ish. It's okay if it's ish because we're going to do worksheets. If you're feeling totally lost, you should probably raise your hand or ask me a question. But if you're feeling like it's kind of making sense, we are absolutely going to practice. Put that up. Everybody, before we go on anything else. Clearly, rule is spelled wrong. I'll get that fixed. So minimum variance, variance of sample distribution sample means are minimal. Standard deviation of sample means measured by standard error of the mean. Standard error is square root of variance. Standard error, how much is the mean off? We'll walk through that too. Have that. No. So your minimum variance formula, and I can certainly go back if you're on the same page. I think you are. If you're not, just tell me. M in this formula is a sample mean for each possible sample. The small mu, M, is the mean of the sample distribution of the population mean. So we're taking the variance, we're taking the mean minus the mean of the sample distribution, and then we're squaring it. And then n to the n is the total number of possible samples. So what we're talking about really is calculating outcomes. So I said, I want you all to think of some random thing or object. What we would be calculating would be like the possibility of you having the same idea or a different idea against the total population of all of you, and the number of combinations of the outcomes. That's what we're looking at today. That so far. We have worksheets, so no worries. See a couple people, eyes glazing over. It's all going to make sense shortly. You can absolutely ask a question here. Well, that's always the mean. So it usually will come in the question, but if you had raw scores, you can still calculate it. Because the mu is the population mean and the capital M is the sample mean, which is always going to be the sum of the values over n for population, or the sum of the values over n minus 1 for the sample. So even if I didn't give that to you, you could still get that. But generally speaking, you're gonna have enough information either to get to the variable or it's gonna be given to you. We can also characterize sample variance with the unbiased estimator. So we can use sample distribution to characterize sample variance, divide the sum of the squares over the degrees of freedom n minus 1. You remember that? That would be the before sample sum of the squares. Remember that's that x minus m, and then we x minus m squared, and then we sum all those, and that equals the sum of the squares, because it's that difference between the value and the mean. Skew distribution rule tends towards positively skewed distribution. So if we're dealing with sample variance, it's more likely to be positively skewed rather than negatively skewed. No minimum variance when we divide the sum of the squares by the degrees of freedom. Remember, variance is how much the scores vary. And standard deviation is basically the square. Sum of the square, the variance of the scores vary. We have the sum of the squares over n or n minus 1. That is our variance, and we square root that to get our standard deviation, if you remember from previous chapters, just to recap. So variance in the unbiased estimator. Suppose we select samples of size 2 from a population of 3 of 2, 5, and 8. We're going to look at the sample variance or the unbiased estimator. So S squared, or the sample, is equal to the sum of the squares over n minus 1, or sum of the squares over degrees of freedom, because the degrees of freedom is n minus 1. This will be more important as we move on. Degrees of freedom is always going to be n minus 1. That will come up. I'm pretty sure the remainder, yeah, I'll go through chapter 12. So we did that right here. So we had 9 samples. We took the sum of the squares over n minus 1 for our sample variance. We sum that, we got 54, and then we divide by 9 samples. And then that means our sample variance was 6.0. So we got these are our different scores. So as you can see for this one, there can't be any other scores in there than 2, 5, and 8. We did the sample variance right here. Got our total of the sum of the sample variance, and then we divide by the number of samples. And that's our unbiased estimator. Yeah. Yeah, so that would be the sum of the squares minus n over 1. So if we take, this is our raw data. This is x minus m. This is x minus m squared. So we have 8. So it'd be easier if we just go like 8. So we have to know what the mean is. We have to do the sum of everything over n. Well, that's going to be 16 over, yeah. So 16, which is 1. So 16. No, 8 minus 1, which is 7. 8 minus n is 2. Okay, sorry. It's early, guys. I gotcha. So this 8 is equal to n. Yeah. N equals 2. N equals 2. Because we have 2 of these, right? So this is equal to 8. So 8 minus 8 0. 8 minus 8, 0. That makes sense?
So the mean was just from those two values.
Just
not
from-
everything?
No, just from these two values. So if we square this, this is 0.
Okay.
So if you divide anything by 0, it's 0. So we can take n minus 1. Yeah. Yeah, sure. So we have AB. What is it? That's 8 and 5. 8 and 5. So let's first figure out what our mean is. So 13 to 6.5. 6.5. So then it's going to be x minus m. So that's going to be 8 minus 6.5, which is what, 1.5? And then 5 minus 6.5 is what, 1? Negative 1.5? Yeah. Yeah, we're gonna get there. Sum of the squares. Yeah, the sum of the squares divided by n minus 1. So. Yep, because so we have to, we're gonna have to square these, right? Yeah, x minus m squared, right? Because we have our values. We have 1.5, 1.5, and we're gonna square both of these. And then we're gonna sum them. What do you have? Okay, so why don't we do that in Excel, guys? That would be probably easier. I think Excel would make more sense. Like this. Okay. Let's go data. Let's go x minus m squared. And then let's get the sum of the squares, and then we're going to do n. That's going to be n minus 1. So what is our data? Our data is 8, 5. Right. Okay. So let's do that. So this is 8 and 5. So we need to sum these. So if we just sum 13, and then we have to get our. So that should be 6.5. So that is equals D5 divided by 2, our mean is 6.5. So x minus m is equal to B3 minus. Does that make sense? No, I've lost you guys. Oh, so I'm just going to take my value minus my mean, and I have that. And then we're going to get the sum of the squares, and then we're going to divide it by n over 1. And then we should have 4.5, but let's make sure that makes sense. So minus H3, right? B3 minus H3, 8. Yeah, so we just did on the board. And then the same thing equals H4 equals B4 minus H3. And then we're going to take and we're going to square both of these. So this is equal to C3 to the second power. And this is equal to C4 to the second power. And if we take these two and we sum them, that's 4.5. Right? Is that 4.5 divided by n minus 1? So remember, n was 2. So n minus 1 is 1. So if we take 4.5 divided by 1, we get 4.5. Does that make sense? At least in the front row, back row. Have I totally lost you? You want to do one more? Would that be helpful? So that this chart makes sense. So what we're doing is we're taking we're doing, this is our, we have a total of 9 samples, but there's 2 in each sample. So we're taking these and we're figuring out the sum of the squares over n minus 1. Now, can anybody tell me why n minus 1 is 1? Because there's 2 in each sample. That's how we're getting our denominator. Does the denominator make sense for everybody? We'll do the numerator in a second. So it's always going to be n minus 1 because there's only 2. Now, if we had other samples, that would be a different n. If I had 2, 2, 2, 3, 4 in each sample, then I would change our denominator, but they're all consistent in this example. So it's always going to be whatever the numerator is divided by 1 because n is 2. 2 minus 1 is always going to be 1 for our denominator. So it says the SS, or the sum of the squares. And the way we always get the sum of the squares is we take the value minus the mean, and then we square it, and then we get the sum of the squares. So because we have 2 values, we have to do it for the whole group of the sample. So if I go back and I say, okay, A and C, 8 and 2, we can all agree that there's 2 samples, right? 8 and 2. So I'm going to put in my data column 8 and 2. Now, we need the mean, right? Now, if you remember, it's the sum of all of them over n. So the sum is 10 divided by 2, which is 5. Sum of values over all of the values. So I'm going to say, so if I take these right here and I just say just the numerator, auto sum, that's 10, but I still need to figure out what my, that should be m. I need to figure out what my new mean is, right? So mean is equal to what? Well, it would be equal to A9, nope, B9, divided by how many are in the sample? 2, divided by 2, so we should get 5. Everybody follow me so far? So then if we go back to our chart, we still got to do more stuff because this is the sum of the squares divided by n minus 1. So we don't have the sum of the squares yet, so let's go back to Excel. Is that better? Cancel. So let's do x minus m. So that is equal to our value of B7 minus G7, nope, minus G8, x value minus the mean, x minus m. 3, that makes sense. 8 minus 5. This one is equal to B2, no, B8, equal to B8. That is 2. That's our next x value. That makes sense. Minus G8, which is that, -3. Right? B8 minus G8. Yeah. Now we're not going to do anything with these yet. These would be 0 because we haven't squared them because of the distance to the mean. Remember, the sum of all the values before we square always equals 0. So we have to start squaring them. So we're going to take this is equal to C7 to the second power. We're just going to multiply it by itself. We're going to get 9. It's going to be the same here. We're going to, because it'll -3 times -3 makes it +9, because whenever you have 2 negatives, you change it to a positive. So we're going to take the same thing. We're going to take C8 to the second power, and we get 9. Now we have x minus m. So now we've squared the difference in the squares. Now let's find out what the sum of the squares is, or SS, sum of the squares. So we're going to take these 2 values and we're going to sum them, which should be 18. So now we're going to take 18, sum of the squares, divided by n over 1, we get 18. N is 2 because there's 2 values, so 2 minus 1. So we just got 18 and then n minus 1. This was our sum of our squares. We know there were 2 values, so we know it has to be 2 minus 1. So that's 18 over 1 Make sense? So we're doing that throughout this entire one right here. And then we get 54. And then we go back and we divide by the total number of samples in, because these are groups of samples. So there's 9 groups that have 2 people. So we divide the all of them, like the sum of all of them, to get our sample or our sample variance, which is 6. No, because we're saying we're dividing by 9 because there's 9 samples total. So we're saying we take each of these, we get our mean, we take our value for each one minus the mean, we square it, we get that sum of the squares, that's our numerator. Then we divide it by n minus 1. This is very easy because it happens to be 2. So we know it's just going to be divided by 1, which means it'll be the same number. If this was 3 of them, we take all 3, get our mean. We would take x minus m for all those, and then it would be 3 minus 1, and we divide it by 2. And then we're taking that value at this point right here, and then we're adding that together to get the sum, the sample variance unbiased estimator. So the sum of all the sample variances right here is 54. And then we divide it by the total number of samples, regardless of how many are in each group. So we have 9 samples with 2 people. That's where we're getting the 6.0. Does that help just reiterating that? If you still have questions, please absolutely ask. Anybody? Yes. Rephrase that so I'm understanding what you're asking me. Then you could do that. Yes. So if we were doing 3, you're saying like 3, 2, 4, whatever. So that would, for each one, the sum of the squares and the n minus 1 would be different, but we could still calculate those for the sample variance. We're generally going to work with like the same amount just for like simplicity purposes, but yeah, that would be, for example, it'd be like, let's say it was 10, 4, 2. You would take the sum of all those, you divide by 3, that would give you your mean. Then you would take x minus m for all 3 values. And then that, of course, if you were to add them up, that would be 0, but you wouldn't do anything with those for summing. You would square all of them. That would give you your numerator. And then n minus 1 would be 3 minus 1, which should be 2. So you divide by 2. And then the next one, it would be, say, 2 samples, same thing. If there was 1, then it would be 1 minus 1, you divide by 0. That would make your variance be not basically, it would 0 it out, like you can see in that first example. Did I answer your question or help make that clearer, I hope? Okay. That's the mu. That's the mu symbol. You can absolutely. Oh, mu. Oh, that's the sample squared. Is that better? Did I zoom in at all? Not really. It's the unbiased estimator. So it's the mean, which is the average, you're right. Sample squared. So remember, if we're doing the variance, we just do the square root. That's why we have the s to the second power. So it's 54. And the whole reason this is squared is because we squared that, the sum of the squares. Like that's why there's a square there. That makes sense. Yeah, we're talking about this. We're talking about the unbiased estimator. But yeah, s squared is sample variance, absolutely. So we multiply the mean by the sample variance, and that's how we get that, and we divide it. And the way we do that is we have to account for the number of samples, because remember, the variance is always the sum of the squares over n minus 1 if we're dealing with because we're dealing with the sample, and it would be the sum of the squares over n if it was population. Does that walk through it? Does that answer your question, or do you want more clear? Oh, I can write it over here. Sum of the squares over n or some of the squares over n-1, we're dealing with a sample.
Yeah.
So the unbiased estimator mean times that, and the way we did that is we accounted for the square, that's our numerator, then divided by the total number of all the samples to get that. So we're trying to estimate. Make sense?
Yeah.
Or not really?
Yeah.
Okay,
Makes
okay.
more sense.
Okay. So we're taking that mean times the sample variance, and we're getting a sense of what it's doing there. Slide. So here's our skew distribution rule. Sample distribution sample of variances tends towards a positively skewed distribution regardless of the distribution in population. So this is literally like a bar graph of the data we just looked at. And if I were to like draw a line over it, you would see that it's positively skewed in terms of what it would look like. If I just took like all the top points there and just literally went like this, that would be positively skewed. So if we're dealing with sample variances, it's a more of a positive skew versus like a normal distribution. So it tends towards that. And remember, we're also dealing with bigger samples, like groups of people that we're getting that from. Variance is just how much scores vary, and they're free to vary once there's one score away from the original set of scores. The reason that you get 0 right here is because the scores don't vary. 8 and 8 are not at all apart from each other. So we can calculate the sample, sum of the squares divided by the numerator, or the numerator divided by the denominator n-1. We're going to get 0 because the scores don't vary. This is talking about how much the scores vary. 8 and 5, 4.50. So it's going to be it's going to look like that graphically. It's going to be a positively skewed distribution because of how the scores vary within the raw data. Making sense? Mostly.
If we just saw like 8, 8 or
You would know that. You can walk through the formula, but we're talking about how much the scores vary from basically each other. There is no variance when they're the same value. It's like basically like a straight line, like they couldn't vary. Yes, so you can like know that. Never hurts to check your math, but yeah, if they're the same values, yeah, that's absolutely right conceptually. There is no minimum variance required, although sample variance equals population variance on average. Distribution of all their sample variances can vary far from the population when you divide it by the sum of the squares over degrees of freedom. Degrees of freedom is always going to be n-1. So again, it trends towards that positive skew, like what it looks like when you graph the data. And when we're dealing with this unbiased estimator, it can be far from the population. So when we look at like the graphical representation where I'm showing you the sample, with the unbiased estimator, it could vary quite a bit. Like it could be far from the population. Makes sense, everybody? We're talking about like the distance and how we're going to infer from that. So you've probably seen these before, but standard error of the mean. So standard error of the mean, we're going to walk through this. So that's going to be, we're going to use theta squared mean to represent standard error of the mean, which is going to be equal to theta squared over n. So the standard error of the sampling distribution is going to be the square root. So the variance, this is very similar. We're going to walk through some examples today in class. The formula is very, very similar to what you're already used to seeing. And then it's the square root for the standard error. The sampling error is the extent to which sample means selected from the sample population differ from one another. I think I can give you like a practical example. So like I would say, look at this again. What we're talking about is how they vary from each other in terms of like what we're selecting. So the extent to which all of the different sample means selected from the same population, which we were just doing the mean right here, differ from one another. So how much, so we're talking about like, these are all different means. This is that positive skew. We're talking about how much they're different. We're going to practice this. If this is making sense, not making sense, etc. You can all continue to ask questions if it doesn't quite make sense to you. And so we use the unbiased estimator. We might actually use this like with bullseyes, for example. Dart hits it on average similar to the sample. Variance equals the population variance on which you divide the sample, the sum of the squares divided by the degrees of freedom. So this is your unbiased estimator at the top, and then your minimum variance on the bottom there. Darts failed at the bullseye, but they are grouped closer together, similar how sample variance varies minimally from the population when we divide the sum of the squares by n. So this is like we're saying, hey, it usually hits a bullseye. That's the unbiased estimator. Minimum variance is how much it minimally varies from what we're doing here, which is our target. So again, we're estimating like, what does the sample do against the population? And the more accurate we are, the less error we have, the more we can make that inference or that broad generalization. If I have a lot of error, probably can't make that generalization, or at least at a minimum, I have to count for that and why it's off, or that could be potentially like a limitation, like there's this much error. And then you might talk about the reasons behind why there's that much error. Like you ever watch the news and they say, oh, they did a survey, there's this much amount of error. The bigger that is, the less accurate they're reporting. So they're like, there's a 10% error. It's not that accurate. 1 or 2%, that's probably pretty accurate of the people that were surveyed. And the idea, like I said, they can never ask everybody, but the sample should be representative of the population. But they can do things like, let's say they're talking about Democrats or Republicans, they can go into a group that's predominantly Republican or Democratic, and they can manipulate that. Like Nick talked about like stats, it's damn lies when you were doing your presentation in chapters 1 through 4. They can manipulate that depending on who they survey. But ideally, yeah, I think that was you. I'm pretty sure. I think it was you. I don't think it was John. I don't think I'm confusing you two.
I remember someone having something like a bell curve.
But I feel like that was one of the guys, and I thought it was you. I don't think I'm confusing you two.
Mine was pretty bare bones, like, I don't know.
Oh, I think you just use a quote. Is that you, Jonathan? I feel like it was one of the guys. Maybe it was one of the ladies, but I thought it was one of the guys. Or was it Carlos? I thought it was one of you two over there. Well, it can be manipulated. Like you want to try to be really like, we have 1, 2, 3, 4, 5. We have 5. Was it 5 women? 3, 4, 5. Yeah, we have 5 women and 4 guys right now. If I wanted something to represent the population, because the guys are less than half, I might want to make sure that you're all in the sample versus just like a few of you, or I might say half of you, 2 of you, and then 2 or 3 women, but not all of them, to try to get a representation of like a proper sample of the population. Like demographics, like accounting for that. Yeah. I could be encoding that wrong. It happens. She dropped.
No, the one who is sitting, who just left.
Oh, yeah, we should ask her who said that.
She was the one.
Then I encoded that wrong for some reason.
Doctor Strange.
Man, that was her.
We're gonna have to ask. That's what.
Well, we'll ask Katie when she comes back. Yeah. What? We're just talking about like stats can be manipulated. Like if I go to a predominantly like Democrat or Republican district, I could have like basically skewed data. Like if you ever hear anything on the news, like now that you understand like a nominal variable is, to say, oh, this thing is categorically great or categorically rejected. That means nothing, because we're just talking about like labels and stats, because it's qualitative. It's just telling you like what a group of people are saying. It's not based like, say, in science versus like a vaccine, like is this much efficacy. We know that it's working, less people are getting sick. So if we took a standard error of the mean, random sample of 100 college students population, state the number of hours spent during finals week, your mean or your average is 20 hours per week. standard deviation is 15 hours per week. So remember, that's the grouping. Like we're saying, that's where the behavior was. So if we said the mean was 20 hours a week, the standard deviation means some students studied 35 hours, some studied 5. To construct the sampling distribution, you identify the mean of the sampling distribution, which is 20. Compute the standard error of the mean. Don't worry, we're going to do worksheets on this if this isn't making sense yet, but you would plug it in 15 divided by the square root of 100. So we're going to square root n. I'll show you that in a, yeah. So where am I getting this from? So we're talking about the standard error of the sampling distribution, theta m square root of theta squared over n. So where is that from? So 15 divided by the square root of n, which is 10. 15 divided by 10 is 1.5. And then you distribute the possible sample means 3 standard error of the mean, SEM, standard error of the mean, above and below the mean. So standard error of the mean to the left and right of that mean, above and below. Yes. Actually, if we go to the next slide, we'll walk through it more and it should answer your question. If it doesn't, keep asking and or in groups. I'll make sure that that's clear to you. So right here, you can see what that is. We took a sample mean, population mean is 20. Compute the standard error. So we had the standard deviation, which was 15. So the theta was 15 because we had the standard deviation, which is 15. So why did this change? Well, because the standard deviation is the square root. So we're not going to square this anymore. So 15 divided by the square root of n, or the sample size, is 1.5. So distribute the possible sample means shown in figure 7.6. So because this was 1.5, 21.5, 23, 24, to the left and right, 18.5, 17.0, 15.5. So this right here is 15 because I was plugging in the standard deviation. This right here is 100 because we look at the previous slide, it's 100 college students, which means it's 1.5. Hopefully that's helping. We are going to practice. Do you feel clearer on that? Okay. There's factors that decrease standard error. Does everyone have this so far? I hope. Okay. Did you have the statistics, Dan Wise? Was that you who did the presentation? We were trying to figure that out when you were out. When we did our 1 through 4 review, were you the one that had the quote about statistics being lies? Was that you? Okay. It was you. Why didn't you say something a second ago? So population standard deviation decreases standard error. So you want to remember this like a rule. As population standard deviation decreases, standard error decreases because it's tied to the standard deviation. So if we have less sort of clumping, that the standard error decreases. So like if there's less variance, there's less standard deviation, there's less standard error. Because it has to do with how far away they are from that mean. So for example, sample size n is equal to 2, selected from 1 of 5 populations, having a population of 4, 2, 9, 16, 25, and so on. So as you can see, the standard deviation of the population decreases. The standard error of the mean, the distance sample means deviate from the population mean, also decreases. Because it's part of the formula. That's why it makes it decrease. Less standard error, less standard deviation, less standard error. Does everyone have that so far? So the next thing we want to remember is as sample size increases, standard error decreases. Now, without even walking through that, why does that make sense? If I ask Alexa something about some variable I'm trying to figure out, and I don't ask any else of you, I'm saying she's representative of a population of approximately 2, 4, 6, 8, 10, 12 people. I'm going to have a larger error because Carlos might have, or Ilona might have another idea in the back or another thought on whatever variable I'm measuring. Maybe I'm measuring things that distracted you, making you walk in late to class, for example. And don't feel guilty, guys. It's not tied to your grade. It happens, traffic, whatever. But I'm only asking 2 of them sort of directly in front of me. Is that representative of what happened on the way here for any of you? Probably not. But then as I start to ask more and more of you and I get closer to that population, of course, the standard error decreases because it's more representative of the total population. Just like conceptually. So the law of large numbers, increasing the number of observations or the sample size will decrease the standard error. The more people that we look at, the more accurate it is. If I looked at this entire population of the class and tried to tie it to DuPage's population, wouldn't be real accurate. If I looked at all the psych majors and tied it, it'd be more accurate. It wouldn't be entirely accurate. If I took half of the population, the larger that is, it decreases the standard error. So does that make sense? Standard error, the mean decreases, so the sample means deviate closer to the population as the sample size increases because it's representative, because it's more people in that group telling us. Sure, yeah. I have a worksheet coming up where I'm literally gonna say, here's where you plug it in and walk you through that. This one was, what did they plug in here? Sample sizes and standard deviation. How did they get the 4 and the 9? I'm going to come back. I'm going to show you. I'm going to show you that on the worksheet. If it still doesn't make sense, then I'll walk through this one. What did they do? They did sample size n is equal to 2. So that'd be the square root of 2, and theta would be the mean. Do they give us the mean? 1 of 5 having. No, that'd be a standard deviation. They give us a standard deviation. Yeah, so the standard deviation is 2.84 divided by the square root of 20, right? No, 100. This was 100 people. So that would be. I think this is given, but sample size n is equal to 2. So it'd be the square root of 2 and the standard deviation, and then it'd be the standard deviation, which was 15. So 15 divided by the square root of 2 is that 4? Is that right? Let's use my worksheets because these are publisher and my worksheets will make sense. If it doesn't make sense after the worksheets, then we'll do more examples. And actually from about chapter 6 on, like it's all me. Like I'm not even dealing with like publishers stuff anymore, or very, very little. It's basically me walking you through like example, math. We walk through our own that I give you, and then you create your own so that it makes sense. I'm a little skeptical of the publisher always making sense. What was that? Yeah, well, I'm gonna, like I said, I have my own examples I think will make more sense. So I think we just kind of talked about that. So the next thing is standard normal transformations. Remember the z is equal to minus. Yeah. So now we're talking about the z transformation, which is, yeah, the mean minus like the sample mean minus the regular mean divided by the standard error. And the standard error is the standard deviation divided by the square root of n. That's what we're looking at. That's where we're this population. So to get this, the standard error, it's the population standard deviation, which they gave us, which is your theta, divided by the square root of the sample size, which in this case, it was 100. I'm not sure if the publisher is using 100 or if they're using 2. That's not really clear. That's why I want to use my examples on the slide. So Z is equal to the mean minus, so the capital M sample mean, small Greek letter mu, regular original mean, over the standard error, which is always going to be the standard deviation divided by the square root of the sample size. But we're going to do worksheets with steps where I say, figure this out, figure out the Z-score, etc. In just a moment here. And depending on time, what are we on time, by the way? Yeah, we'll probably take a break before we do the worksheets. And we were right about here, right? So the first thing we do for the Z transformation is we transform the sample mean into a Z-score. Locate the corresponding proportion for the Z-score in the unit normal table. So we're going to be referencing the unit normal table. You guys remember the unit normal table from about a week ago? I posted that in the classroom. We're going to use that today in class with our worksheets. And that takes us to the end of the slideshow. So how's everybody doing? Do you need a few minutes to just kind of digest? Let's call it, you want 8 minutes? Is that what you said in the back? 6 minutes? What do you guys need? 8 minutes, the Fibonacci number. Cool. Yeah, let's do 8 minutes. Yeah. So 24, 25 after or so?
You still haven't like sent me like the code yet.
It doesn't need the code. It's supposed to be in
Yeah, I tried
in
like
here.
I tried both of them. The same thing happened to me as well. Then
Let me make sure that I'm not screen sharing. I don't think I am. Yeah. Perfect. Okay. So
because they saying like saying like saying that can you explain me about the whole instructions, even though I just told them I plug in like the 2 codes.
let me see if I can find. That doesn't make any sense, what she's saying. Let's call her Ariana because it should just work. I understand why it doesn't work. Let me save her number. I have her number in here somewhere. Can't stand when they don't put their numbers in here. Right, so let's grab. Where is she? Why does that not work? All right, so let's go like this. So did you did register, right?
Then I put like the two codes.
You tried.
I tried.
Can you show me your codes? Because I feel like there was, so you got,
This one is for the electronic, which is this one. I tried it first.
that's Sage.
Mhm.
And then what is, what, do you try the WebAssign? one?
Yeah.
Which one?
I also tried this one too.
So she needs to update. Did you try it without the Sage
Mhm.
RMY? See
I-
that access? Did you
I
try, did you
think I
try,
did.
did you try with J? Trying to find her number. No.
Because I feel like it's way.
Very interested. And you try, and you tried it with Sage,
Yeah, that's
everything. So try it without the word Sage. Just see if that works.
So just
Try
the
US dot. No, and you tried it with Sage, right?
yeah.
5258 WCNN JMBK.
Because I feel like it's the same that happened to Vale too. Because Vale also had like the
But I thought he got it worked out.
yeah, but he just emailed them to change the code.
So email, so can you, do you see this right here? You want to take a picture? Email this person what's going on. You can CC me.
Mm.
She should be able to fix it. You can grab her information. She should be able to fix it. If not, Nicole will be able to, and I can put her on the email too. Or, yeah. Email her, and then let me see if I have her phone number. Okay, let's see. I don't have a phone number.
So I should have.
Wait, I got a phone number. That number, that she, I think she must be local.
Mhm.
She should be able to help right there, 630.
So I just say to change my code ring.
Yeah, just email her or call her and tell her what's going on
Mm.
and tell her that you have the code from WebAssign from the bookstore and read her any or all those codes and she should be able to fix it.
Oh,
If she can't fix it,
Mhm.
tell me, you can totally see me on the emails, but she should know how to fix the code.
Mm.
If she doesn't, Nicole, who's more senior, will know, but Argiana, she knows Nicole.
And then yeah.
And then I'll just give you more time if you needed to get caught up on WebAssign.
Yeah. So it's just like my parents right now have like a 2-week vacation.
Okay.
So when is the test? Is the test like the following week?
The fall should be the fall. So the test should be approximately a week to a week and a half from now,
Okay.
because it'll be on chapters 5 through
So
8.
it's gonna be like
Probably this time,
Wednesday?
probably Wednesday of next week, or like by Monday of the fall, because we want to get through chapter 7 and 8.
Mm.
And then I want to give you a chance to all at the hard deadline of presenting that. But I
Mm.
think I'm pretty sure I have an exam to review worksheet too.
Okay.
So we're gonna want to go through all that before you actually have to take the exam.
Mm.
So approximately about a week or so from now, and then the last exam will be chapters 9 through 12 towards almost the very end of class.
So it's only like 3 chapters, right?
4 chapters.
Okay.
So it's 4, 4, and then 4, but they're non-cumulative.
Mm.
So you still need to know like the foundations for 1 through 4, but I'm just testing you on 5,
Those
through- 5 through 8, and then 9 through 12.
Okay.
So approximately then, and I'm sorry I have to give you a clear answer. It's just I want to make sure we get through it. Approximately about a week and a half, maybe 2 weeks from now, we'll have another test, and probably 3 to 5 weeks from now, or 3 to 4 weeks from now, so like towards the end of the month would be the last test. Usually there's a little bit of leniency and when I have the final grades posted. So if I can give you all a little more time, I might say, take the last exam within right after the semester, or I might say by the end, depending on what we get through.
Okay.
But I'll post an announcement and I'll give you guys typically, if I can, I'll give you like a week to study from when we do our review day.
No.
So that way you're prepared. Make sense?
Yeah.
Cool. Yeah. So the problem with WebAssign is because it's an electronic code, you're like, well, it's 2022, just email it to me, right? That makes sense. But it's actually something physically you pick up from the bookstore, which is an electronic code on a sheet of paper. And if you want to come over here, I have Gustavo, can you hold up your thing that says WebAssign and show it to Nick? You want those things? And they're still not working? Okay.
Yeah, because those are the original ones that like with the numbers I gave the person I talked to when I gave them like the.
Do you have-
digit code. I don't have it.
Do you have your cell phone with you?
Yeah.
Come over here. Why don't you take a picture of this information right here? Because she'll be able to fix it. And then what I can, because I can't fix the code, but this lady right here at Cengage, she can fix it.
Which one?
Argiana.
Okay.
That's her email. And she's local because she's got a 630 number. If she can't fix it, Nicole will know how to fix it.
So there's nothing, so do I need to go to the library still if I, or to the bookstore if I already, because when I got, so it came with the book and then it came with the,
And it looks just like his.
yeah, like the red one right there. And
That
then
says
the
WebAssign
other
and then
piece
you
of
open it as
paper.
electronic code in there.
Yeah, the 16 digits. And I sent that to the person we were in.
Then let's get
email
Nicole.
with, but she said it wasn't a Cengage code.
Cool. Cengage. Please tell me it's
That's why I was
here.
confused. I'm like, did I just go with the wrong code or something?
No.
It was in like one of the earlier ones.
Oh, you sent it to her.
yeah, and she said it like
the hell?
wasn't something, right? Like she said it wasn't a Cengage code or something. So that's why I'm like,
I need. I'm just gonna call her. Because this is.
that's weird. I've never had this problem with Cengage. It seems like multiple people in the class are having. Is it just like an issue with this particular?
Usually it's pretty smooth sailing, but what we can do is let's call 630-864-9781. Let's see if she picks up. Because then I can just solve it for you guys right now.
Should I stay here? Or sit?
Yeah. Either way.
Hello.
Hi, Argiana. This is Jason.
Hi, how are you?
Good. How are you?
Good. What's going on?
I have two students that we've been emailing you. Maybe you can grab Nicole about their Cengage codes not working. The problem was that there's something wrong with the code. Maybe Nicole needs to fix it. But I have two students that went and physically got their code from WebAssign from our bookstore, and their code is not working. And they've emailed you, and I know it was the holiday. Maybe you're all busy, but I really think you or Nicole could fix that because they are definitely Cengage WebAssign codes that have WebAssign's name all over them with the electronic code, and they still don't have access to WebAssign. That should be for both Nick Little and Gustavo, and you should be on those emails. Can you help me out or get Nicole involved? Because she'll know.
Yeah, I asked for some information yesterday. I haven't heard back from Gustavo. I didn't see an email come in about a student named Nick. But I did answer Gustavo yesterday. I needed information on his code. So me and Celeste both emailed him back.
So did you get emails, Gustavo, from Celeste? They need information on your code. Make sure you reply to them and maybe list all your codes you have from WebAssign.
Yeah.
So they can
if-
identify what code, and then I would say do the same thing.
Yeah, because me and Celeste are just trying to figure out if it's a Cengage or a Sage code. So that was the request that we sent for him. I didn't see an email come in for a student. What was his name? Nick?
Nick Little. I do see that he sent an email a while ago directly to
Yeah,
you.
so the last email I have for Nick is somebody telling him he needs to go to the bookstore to pick up his code.
But he
So I
did.
don't have any. Yeah, I
And-
don't have another email though for him saying his code didn't work. Do
So
you want to forward it to me though?
just can you forward me your code or send it to Adriana and I, say, here's my codes. I would say both of you, like, anything in there that has a list of codes, put them all in the email. So that way, if it's a Cengage or a WebAssign, you can hear me, right, Gustavo? You're paying attention to what I'm saying, right? And CC me on the email, and then she can get the more senior rep together. And then what I can do is on my side, I can give you guys like a several day leniency or a few day leniency or whatever until they get you access. So you have time to go into WebAssign and get it done. I would email her, but I would put all the codes you got from the bookstore. I would list them. I would be like, this is a Sage code, this is a WebAssign code. Like I would just, and make sure you have all the letters and all the numbers, double and triple check your code to make sure you're not typing it in wrong. Maybe take a picture of it and attach it. But I would, if there's like 2 or 3 codes in that pamphlet, I would probably send them all because it's probably one of them that's right.
So on my one phone, it told me to go to the website and take
Yeah.
URL to Cengage, but it does say that it's Sage.
What should the code start with? Do you know, Adriana?
I'm not 100% sure.
So just
It
email,
should be like,
go
yeah,
ahead.
like 10 digits or so. I
Should be
think.
10 digits or so, but if, like I said, if you have multiple ones and they're all 10 digits, just
Yeah,
email,
if you could just send a picture of
Just send-
all of them, that would probably be best.
yeah, send, or take a picture and attach the file as like a JPEG, send it to her and like CC me on it. And then they should be able to figure out which codes make sense for you. And that should solve it. I'd be happy to circle back with either one of you like Thursday or like tomorrow or Friday, like in a day or two, or meet virtually or something if like it's not happening. But I would imagine, because they're pretty awesome over at WebAssign and Cengage, that you would know in 24 to 48 hours. Is that a pretty safe assumption?
Oh, yeah, I mean, if they get them over to me now, I'm happy to look into it. Like I said, I didn't have any email from Nick Little. I just had that one from Gustavo yesterday, but yeah, me and Celeste were both on it. We just needed the code. We just need to figure out if it's a Sage or a Cengage code, because
Okay.
that will determine if the bookstore needs to give a new code
Okay.
or if I can provide a different code.
Okay, so make sure Celeste is on that, Argiana's on that, and I'm on that. And just take a picture of all your codes that they ever got you related to the material. And then if it's a bookstore issue, the bookstore will fix it with Celeste. If it's a Sage or Cengage issue, they'll fix it. And that should resolve it for everybody. And I know if it's on their side and the code's bad, they can change the code if they need to. And I think, and I'm pretty sure from what she's telling me right now, that the bookstore can do the same thing. So as long as we know who kind of owns the code or what the problem with the code is, they should be able to fix it.
Correct.
What was that?
Yeah, it's all good.
Okay, I see it. You should have an email from, oh, okay, let me forward you this from Gustavo. You sent it to Celeste and I, which is fine, but I'm also gonna send it to Argiana. So there's that one. And then if you want to send it, Jonathan, I'm sorry, Nick, you can confuse it. If just when you get home in a few hours, send it to me. Like I said, it should be Celeste, me, and Argiana, and then we should be able to fix it. If you miss somebody, I'll forward it. If you want to text me, either one of you, like when you sent the email, because I'm not always in front of my email, I can maybe expedite forwarding that over to them if they're not all in the email. I could just be like, hey, I'm an hour away or whatever, where I could text you back and be like, hey, I've sent it over, but we could definitely get that done 2 days before the day's out.
Okay, yeah, I'll make sure.
Yeah, so just looking at this code, Dr. Mack, by the way, it does look like a Sage code.
Okay,
So the best bet would be to, I can forward this along to the bookstore, or it might be best if you reach out to Celeste, or I can just like copy and paste this and reply to her email.
that would be
but-
wonderful. And I think he actually initially sent it to Celeste and I just forwarded it over to you, but that would be fine.
Okay, great. Yep. So I'll forward it over to her and just let her know that that you guys need some assistance, and hopefully she can help you guys out quickly.
Okay,
Fingers
perfect.
crossed. She was very responsive yesterday, so I hope as long as she's in the office, I think she can help pretty quick.
Okay,
Okay. All right. Well, I appreciate your call, and just let me know when if you get an email from Nick and I'm not copied, just forward it along, and I'll definitely try and help you guys out. But I'm assuming Nick will have the same Sage code if he purchased through the bookstore. So definitely copy Celeste and myself on there.
okay. Everybody got that? That should solve it. And like I said, I can, on my side, give you a little bit of leniency to get caught up. And everybody else is good, right? It's just you two? which is 100% fine. But is there anybody else that is having web design issues that I should tell them about right now, as long as they're on the phone? Everything's okay. All right. Okay. I'll watch for follow-ups, etc. And I'll talk to you all soon. Thank you so much for being available and answering the
Perfect.
phone.
Thanks, Dr. Mack. Have
Well,
a great day.
You too. Bye.
All right, bye.
Okay, cool. So we should be on right here. Statistics. Student resources, in-class activities. I think we're right here. Is this it? Homework. 629. Is this it? I think that's right. Make sure. So that. Okay, so what we're going to do is we're going to do the other half of this worksheet from 629.22. So it should look. So you would have already done this, and then we left this one alone. So we're going to do questions 1 through 6, and then question 7, SPSS. We'll do that on your own. Now I don't have my book with you, so if you get stuck on number 1, I'll walk you through that on Monday if we need to, just so I can see it too. I'll see if I can pull up, if I can pull up the electronic version, which I think I can. I'll walk you through that today. I'm pretty sure I can pull up the electronic version on my side. And then we're going to do the comprehensive tutorial document found in Blackboard, I think to like crosstabs roughly, but I'll come around and I'll help you. So we're going to go through like 7-8 questions, and then we'll do an extensive chapter 7 review on the formulas by hand. And I'll go through the answers with you guys. I'll give you like maybe till 11 to work on it or something. 629. So I think we started it, but I didn't make anything due yet. So you're just going to click on student resources, in-class activities. Yes, Katie.
Is there a way you can do like the first, like 3 questions with us?
Yeah, absolutely. So it should be, it's not folder B. No, it should be. Actually, I'm thinking maybe, let me just see something. Yeah. Let's do that. So let's work backwards. I'll pull up the answers. We'll make sure the publisher has their act together, and then we'll walk through it. Chapter 7. Can everybody see that okay? Does everyone have this worksheet? Did everybody find it okay? Or so it's 629, it's the second half before we could do any SPSS stuff. Is the 629.22 worksheet under in-class activities that we never turned in yet. We did like the first half. So this one, the first question, so it says, can you all see that okay? Is it zoomed in enough? Suppose a researcher wants to learn more about the mean attention span of individuals in some hypothetical population. Researcher cites the attention span time in minutes attending to some task is normally distributed. So they're saying there's a normal bell curve on the following characteristics: 20 plus or minus 36. Mean plus or minus standard deviation is what that means. Whenever you see it listed like that, Based on the parameters in the example, answer the following question. What does a population mean? Does anyone know what the population mean is? Because we just gave it to you. 20. So if I go down here and I look at the answer, 20, that makes sense. What is the population variance? Standard deviation, but this is theta, it's squared. So we're going to square root it and we're going to get 6.
Population variance is gonna be this.
Yes, the standard deviation is without the square because you take the square root of it. So just based on what it tells us, we're going to square root it to make it theta by itself. Well, the square root of 36 is 6. You could use your TI calculator. You could use Excel. I mean, if you could literally take 36 and then you just go equals SQRT like that. Grab your number and the other brackets. It's going to tell you that it's 6. Yes, and we're going to square root it. So let me go back. What is the deviation? It's because what is a population? What is the population variance? Plus or minus? Did they do that wrong? Plus or minus? Yeah. So they gave us the variance and we need the standard deviation. Is asking us the population variance squared. So they gave it to us backwards, I think. Population variance. I feel like that should be what is the standard deviation? Yeah. See, that's what I don't like about publisher worksheets. They make mistakes like that. What is the standard deviation? I'll change that on the next class. The square root. They wrote that funny. I can update the original or you can type that in there. That should be standard deviation. The problem with the publisher is they don't have the advanced training. I'm going to catch errors like this. They're not going to catch errors like this. They're usually like people with like masters, like they're usually pretty educated, but they're going to miss small stuff sometimes. It'd be without the square because we're taking the square root. So I should change that to, it should be more like insert symbol, more symbols. Oh, I'll just go like that. We'll just like that. We'll just grab this. Oh. Use pictures. Well, that's fine. We'll just do the other document. Chapter 7. Other document? No, we don't. Yeah, so it'd be theta. I'm just trying to find where we add that. I think that's symbol, more symbols. More symbols. I mean, this is probably as close as I'm going to get right off the top of my head. That just, it depends. I'm telling you, it's here in the symbols. If I go like that, that's not exact, but that's the idea. That's fine. I could do that. Just go theta symbol. somewhere like pictures. Well, not really, but you get the idea. Sketch the distribution, make sure you draw the shape. Plus, yeah. So this, the normal distribution with a mean of 20 and standard deviation of 6. That's, what was that? You could do that too, yeah. Yeah, that would probably be way easier. But it's an image, but that should be okay. If I don't have it lock up on me.
It's supposed to, but they didn't meet.
So the mean of 20 and standard deviation. So like, that's literally just asking you like. Number 3 is just like, draw it. That's 20. And then your standard deviation would be 26. And what, 14? Your standard deviation is the left and right. And then if you want 2 standard deviations, it would be 6 less, 6 more, 3, and so on. That's what number 3 is. Number 4 is 20. Now, how do they get, what does it mean of the sample distribution for a sample size of 4 from this population? So the mean of the sample is what we have. So that's 20. Yeah, because they gave it to us again. Like, they literally just, what does it mean of the sample? They gave it to us. So this whole 4 is like throwing us off because they gave it to us up here. What is the mean? This is the mean, the 20 plus or minus. What? If you want to, or you could just literally take this. You could cut and paste like this right here. Copy. And paste like that. That's probably better. So what is the mean? What does it mean of the sample distribution for sample size of 4 from this population? That is throwing you off. We're going to use that in the next question. No, the sketch. So 1 is because the population mean, and then it asks you again, but we know what it is because it tells us here. So like question 2 and 4 are like the same thing. It's asking you what the population mean is, but it gives you this note, which is the mu. So it's basically just telling you where to find it. It's always going to be the mean, and I need another mark, clearly. It's always the mean plus or minus the standard deviation, or the mean.
Yeah.
Yeah, so it told us that it was 20 plus or minus 36, but it gave us the variance because it gave us theta squared. So we know the standard deviation is 6. So it's 20 plus or minus 6. So that's plus or minus 32, 8, plus or minus that standard deviation. So number 4, we're just going to grab the mean again because it gave it to us. Does that make sense, everybody? We're going to use the 4 later. What is the standard error for the sampling distribution? 6 divided by the square root of 4. Does everyone know how we got standard deviation divided by the square root of the sample is going to be this? So we're going to take the Greek mean we're doing so we're doing the standard error or the SEM, which is this, like that, is equal to the standard deviation over the square root of n, which is equal to 6 divided by the square root of 4, which should be 3 because the square root of 4 is 2. Does that make sense, everybody? Ish, yes, no? So sketch a normal distribution. So what does it say? Based on your calculations for the mean and the standard error, sketch the sample distribution taken from the population. So this is assuming normal distribution. And you're going to include the mean plus or minus 3 standard errors. So the mean is still 20. And the only difference is that we're gonna say 20, okay? And then we're gonna mark it 3. So so 1 standard deviation or 23. And this would be 1 standard deviation to the left or 17. It does, that's kind of how I would probably put them at the bottom, but I probably wouldn't take points off if you did. Oh yeah, I probably put the bottom. Because really our X values are our X axis and our Y values are the frequency. So I would really put them at the bottom. It's with a standard error of 3. Standard error of 3. So SEM, standard error of the mean, SEM. You're just labeling it instead of standard deviation, you're labeling it like SEM, standard error of the mean. So first we did standard deviations, which is that square root of that variance. And then we're drawing it again, but we're using the standard error. And we're talking about where the standard error is in relationship to the mean. So one is the standard deviation relationship to the mean. The other one is the standard error distance to the mean. That's what we're drawing. And just mark it accordingly. That one is standard deviation, one is the standard error. So number 7 is going to be the Z formula, but let's make sure we're all through 6 at this point. This, when you've drawn that, maybe like say something, and then we'll do 7 and 8. If that's right. I think I only had 7 on my actual worksheet though. Yeah, we're just going to do 7. Yep. Enable editing. Cancel. All right, so this should be the Z transformation. So let's do the Z together. Z is equal to what? Over standard deviation. Oh, wait. The standard error is, what is probability? No, you must complete the Z transformation for the sample distribution. Yeah, then for the unit normal table for the answer. Remember the sample population for the standard error we calculated to be 3. So that should be just should be. Right. So unit normal table. I'm pretty sure we're using the Z formula. That should be right. So that should be, where is that? Where's my Z-score? Z-score? No. Oh, the unit normal tail, I think is in example 4. It's chapter 4. No. Unit normal table. Chapter 6. Helpful Z table. Yeah. That's what I did, right? Z table? No. So this one. Yeah. Let's see. Yeah, that's right. So we're trying to do the problem. So what we're doing is we're doing X minus M divided by the standard deviation. So 23 minus 3 is 20 divided by 3, which is our standard error of the mean. SEM. Yeah. 3, which is 1. Z is equal to 1. And then we're going to go find 1 right here. And P is equal to 0.1587. So we're talking about the probability. So we're looking at the area in Z beyond the tail. And if we go back to a sample mean of at least 23 minutes. So that would be greater than the mean. So the reason that we're looking beyond, because it would go beyond. So let me see if I can show you what that means. Like, the reason is we're not looking between the Z and the mean. We're looking at the probability because we've normalized the score to represent a Z score. So the Z is the standard deviation. So we're saying it falls right here. And then what's left over is our probability, which is the P is equal to 0.1587. That doesn't make sense to you. Let's see.
I don't like how they like highlight the areas yellow and like they don't
Highlight this.
Yeah, like
They don't, you know what? They should really highlight this,
that would make it, yeah.
which, yeah, that would make it easier.
So is it that? Yeah.
7, because we're finding like, where's the standard deviation? And then what's the probability towards the tail of getting to your standard deviation being greater than what our mean is? Does that make sense? Probability, yes. Over the standard error of the mean, which was 3, not the standard deviation. We're going to do that in a second. I think the scenarios that I have coming up for you are going to explain that, which would be right here. Let me see. I think I have that. The mean. Pretty sure I have. Mean minus. Oh, you know what? You know what? This is going to be. Let's do it like this. Let's do mean minus mean over SEM, right? That's the other formula. So 23 minus 20 still equals 3 divided by 3 is 1. Sorry, I put the wrong one up there just because we're doing both. Mean, yeah, sample mean, large M minus original mean over the standard error to convert to get to that Z score. Yeah, that's right, because that's the sample mean. Capital M sample mean, lowercase, which seems backwards, population mean. So we're taking the new mean minus the old mean divided by the standard error of the mean, getting the Z score. Then we're taking the Z score, looking at our unit normal table and going over to C, which is the remaining probability because we've normalized it into a standard error of the mean. So how much like the mean's off. And then we're saying the probability of getting to M equals 23 is 0.1587 or 15.87%. Because remember, under the curve is like 100% or 1. So we're saying basically like what's left over in our probability. And I still agree with you, Katie, that that it would make more sense if this was shaded on the third example, because I feel like it's confusing without seeing that. Makes sense? What? Yes. Hang on. Let me see. Did I ask for a graph? Yeah, that was what you did on number 6. Yeah. Number 6 and then number 7. So it's mean 23, M, large M, minus old mean, small, like the Greek mu, 23 minus 20. Yeah. Z, mean minus, so 20 minus, sorry, 23 minus 20. Do you know where I got these from? The actual graph, I have it right here. I can draw it again, bigger, yeah. So that's 20, which is our mean, right? Or we can say 20 down here, mean. And then our standard error of the mean, it happens to be 3, which means the value is going to be 17 and 23. Because the standard error of the mean, it's kind of like standard deviation. We're talking about the error of the mean. Like when it's off. I have practical example. Yeah. Shade to the right, yeah. That would make more sense. I'd be happy to email them, the publisher, and be obnoxious about it. That'd be fine. Yes. You could, but I would stick with the formula that I gave you. Because like if it works, it could work on a test. I don't want to tell you that that's always going to work. I would still rely on the formula, but yeah, if that's we're gonna have a spot check that with a few more questions before you start using that, because it could just be.
Which formula are you using? Is it the?
Oh, I see what you did. You took the mean plus the standard error. That would make sense. Yeah, because that would be the left or right. I would still use my formula because you want to deal with the standard error of the mean, but technically, yeah, that would still work. What was your question?
Which formula are you using?
Sample mean minus population mean over the standard error of the mean. And the standard error of the mean is divided by so I have to get the standard error. I have to take theta or a standard deviation divided by the square. So this is good. So I'm using the standard deviation divided by the square root of n to get this, and then I'm plugging this in to that.
So you said it's sample mean minus population
Mean divided by the standard error of the mean, or OM. I think, yeah, that's question 6. I don't think I asked you to draw that. No. I want to see if this will work. Maybe. Oh, that will work. Okay. What page? (227) (228). That's our standard error of the mean. Theta mean. So this is always going to be equal to standard deviation about the square root of n. And then we're going to take that and plug it in to this. So z sample mean minus regular mean over the standard error of the mean. I wrote SEM or this like the Greek notation.
That's the notation.
And that's the notation. Ooh, not quite.
It's 272.
Cool, then I can walk you through it. So we're literally going to follow the directions step by step in SPSS, and we can walk through it as a class. Does everyone have SPSS, or can you load SPSS if you haven't already? So let's grab SPSS. I'll zoom in as much as I can for SPSS. We're actually probably going to delve into chapter 8 today. We probably have time, as daunting as that might feel. But we'll take a break before we get into chapter 8. So open up SPSS if you haven't already, everybody. I know it's a large program, should take a moment to load. SPSS. If you have a laptop, that's the best way. I have 2 monitors all the time. I get freaked out when I don't have a second monitor. Yeah, so just new data set. And then we're just going to follow the step-by-step direction of the book, and we'll do that together as a class. And then we'll do a couple things with the other one, but it's pretty easy. So I think I said, oh yeah. And then we're gonna down, then what we're gonna do is we're gonna take the Excel file and then we'll open an SPSS and just play with it a little bit, and I'll walk you through that. And then that'll complete this worksheet. So we're gonna do 272 apparently, by the way, if you have the ebook, 272. 272. To 273. To 273. Need 2 to 273. And then you should have something that looks like this. 227 to 220. Yeah, 272 to 273 in the ebook, which should be included in your WebAssign. It's page 227 if you have a paper book. Okay, and I guess I can zoom in, which is awesome. Almost too much. All right, so the sample error is real similar to the formula. Just look at sample error is equal to the sample sample standard deviation divided by the square root of n. So we're going to do SPSS. So first, we're just going to enter data. So we're going to calculate the standard error for a team of 10 firefighters that respond to an emergency call. So the times are 93, 66. So we're going to enter these, but first we're going to click on the variable view tab. We're going to type in reactions. We're talking about the reaction time, so we know what we're looking at. So we're just going to label our variables. So we're going to do variable view, and we're going to type in reaction for reaction time, like that. We're just going to type in the word reaction on your variable view tab in SPSS. Just make sure you've done that so far. What?
I wish Einstein bagels.
That'd be awesome. And just type the word reaction in variable view. And let's make our decimal 0. like that. So just decimals, 0, and reaction. If you want to type reaction time, I'll take that. But SPSS thinks that spaces are illegal, so you gotta do underscores if you type that. I'm just saying type reaction because it's simple for reaction time. And what we're talking about is the firefighters and let's not, let me look at it. Okay. There we go. So we're going to type in, okay, I think that's probably easier. You guys can see that better, right? So we're clicking the variable view tab and we're just labeling it for the reaction time. And what we're talking about over here is the time of firefighters to respond to it. Yeah, here we go. That's fine. So now, so let's just say these are in seconds, maybe, because minutes would be kind of scary. Otherwise, the building's going to burn down, right? So let's say these are in seconds. So we did the variable tab. We typed reaction for reaction time, or I'll take reaction time. We did the values. Then so we made that to 0. Now we're going to enter the values in the column. So 9366. So data view, reaction 93. 66, 30, 44, what is it, 20, 100, 35, 58, 70, and 81. Does everyone have that, or take a few minutes and enter the data? Yeah. So all you do is click on variable view and change your decimals to 0 right there to the right. And then when you click on data, it'll automatically update it. And then just everybody get those values in there before we do anything else. And then we're going to estimate the standard error of the data. So, and we're getting these, we're literally getting these numbers right out of the book. And while you guys are doing that, I'll go ahead and share our screen here and do this in SPSS. So that way you guys can all see that for the recording. Okay, so we got SPSS. And I'm just going to basically do variable view. I'm going to type in the word reaction. And I'm going to make this 0 decimals. And then I'm going to click on data view and I'm going to type in the numbers, which are 93, 66, 30, 30.
35, 58, 70, 81.
Perfect. So then the next thing we're going to do, which it literally tells us, we're going to click on analyze descriptive statistics. So we're going to go analyze descriptive statistics and then descriptives. So analyze descriptive statistics, descriptives. And you get that dialog box. We'll do that on the other one. Analyze descriptive statistics, descriptives. Then we're going to take and we're going to move reaction into here. Should be right. I think that's probably what it says. Yeah, we're going to move the arrow to the right. And then we're going to click on, I think it should be options. Yeah, options. Standard error of the mean. We really are just doing the standard error of the mean. So that's all you have to do. So options. I'm going to uncheck. I'm literally just going to ask you for the standard error of the mean and continue. And then either run or okay. Same thing here. Continue. Okay. And now it gives us the standard error of the mean, which is 8.596. You just click continue and then okay. And then of course, you're gonna want to save your data as a save file and an SPV file for like output for your upload. So it's analyze, descriptive statistics, descriptives. This is gonna be over here. You're gonna move the variable with the arrow key like that. You're gonna click on options. And then all you have to do is click standard error. That's the only one we're asking for. And then you're gonna click continue and then okay. So see, SPSS will save you a ton of time, but as a SPV output file, so file, save as, and then it's going to automatically give you that, and then label it like exercise 7.7 something, so we know what it is or like that. And then the other thing we're going to do in a moment is we're going to do a little bit of bringing the data in and using the comprehensive document just to do a couple things, but we're not going to do the whole comprehensive document, which is why you should watch the recording and come to class, because you probably end up doing more work if you weren't here. As a separate file, you'll have multiple uploads, because what I'm doing is when I'm checking your homework, I'm looking at, did you do the work like in Word or Excel, depending on what we're doing? Then I'm pulling up the file and I'm saying, did you enter the data in and label it correctly? And then I'm going in and I'm saying, did you get the output and did you get the right answer? So that's why I'm saying, put that all in there so I can see you did the steps. Yeah, Carlos. It should, yeah, if you've downloaded it and saved it, yeah. And you might have to send it to yourself. We're going to do this, and then we're going to do like a couple steps for number 2. And then we're going to practice by hand the stuff I said on chapter 7. And then, like I said, we'll probably walk into 8 because we probably still have time. We're still at about 90 minutes or so. So we should be able to get through the SPSS. So we have time if you want to save it or ask a question or have me show you that again. And then, like I said, we'll walk through a couple of problems on probability. Then we'll take a break, of course. We're gonna have at least 2 or 3 breaks, always. Or we can do it after SPSS, but I feel like if we get through all of chapter 7 and take a break, it'll be a little bit more clear. But if you're feeling like falling asleep or need a few minutes of fresh air, just talk to me. Does everyone have through 7.7, or does anyone want to see that again on the firefighters before we do the next thing? Just upload the file. If you want to write something on the worksheet, right? I did this in SPSS, but no, you don't. Just because what I'm going to do is I'm going to stop on Word at that point, and I'm going to look at what you've uploaded. So no need to do that. And then the last thing, and if I like, just talk to me in terms of the pace here. We're going to do something with the data that I gave you. Now, the data that I gave you is absolutely no big deal. That's right here. Blackboard.cod.edu. And then we're going to go in here, student resources, in-class activities. We're going to go to 62722. And then you have desktop, Baltimore City employees, and it's an Excel file. Click on that and download it. And I will stop sharing and show everybody on here what I just did again. Desktop, share, and then let's go to blackboard.cod.edu, and we'll go. This is real data that I got off a free data set. So we're going to click on. You could. So we're going to click on student resources. And then we're going to click on in-class activities. We're going to go find 622, and that's 629, I think. 629, yeah. The first one, not part B yet. And then we're gonna click on desktop, Baltimore City employees, download the file. And then we're gonna do SPSS. And I'm gonna close my output file because I've already saved it because I want something new. And I'm gonna go File, New, Data. And I'm just gonna get myself a brand new save file. And that's the same thing here for everybody watching. We're gonna go make sure that I downloaded that. Download. So then we're gonna go into Excel. File. New data. And then say that. And then we're gonna go File. And I'll show you on the other screen in a second. Import data, Excel, File, import data, Excel. And we should get a pop-up. And then we're just gonna go grab the download and open. Same thing over here. File, import data, Excel. Where is it? Is it in my downloads? Downloads. I'm gonna grab the file, click open. And then don't mess with this, just click OK through it. Okay. And then OK. And now we have a whole bunch of data that came in here. Just click OK with the pop-up. Just click through it. And then you should end up with a bunch of data that we got from Excel. From the file that I gave you. So we basically taken an Excel file, open it up in SPSS, and then we're just going to do a couple things with the, yeah, you have to download it to upload it. So download the Excel file and then open it through SPSS by importing it as an Excel document. And I can show you guys that again on the screen if you need me to. General.
Yeah, there you go.
And we're just going to do like 2-3 things with the data, and then we'll save it and export it. Then we'll work by hand. So the document that I'm using is as like a guide here is under general tutorial. So student resources, general resources, SPSS tutorials. If you want to follow along here, general tutorial, which is the comprehensive tutorial right here. And we're going to do the summarizing data. And then we're going to do the frequencies and a bar chart. And then that's it. We're not going to do crosstabs. We're just going to familiarize ourselves with just a couple steps with SPSS, which I'm going to walk you through. So the first thing that we're doing is analyze scripted statistics, and we have current and beginning salary. So we're going to grab something as close as possible to that. Analyze descriptive statistics, descriptives. Let's take gross salary. I think gross salary would be probably fine for what we're doing. And then let's ask it to tell us some stuff about it. So we'll just take gross salary options. Let's do mean, standard deviation. Yeah, we'll do that. We'll do all of those. Let's do mean, standard deviation, variance, range, and standard error, because we're pretty familiar with that. I did gross. Just like the gross income from the file. How did I get there? It was analyze, descriptive statistics, descriptives. I grabbed gross, arrow, options, and standard error of the mean. Let's grab the variance and the range too. And then we're going to click on OK and OK. And then we're gonna let it spit that information out for us. File. Let's see, analyze, script statistics, descriptives. And we're gonna grab gross, move that over. Options. We can grab variance and range too. That should be fine. Continue and say, okay, we get a nice SPV file. Next thing we're gonna do is not yet, because we're gonna do a couple more steps, then we can save it. And then the next thing we're gonna do is the frequencies. So we're gonna go analyze script statistics frequencies, and we're gonna try to grab something like employment category or something real similar. Because this is not identical to the data, so we're just like working with the data a little bit. So let's go back in here and we did employment cat. So analyze frequency, script statistics frequencies. Let's do, what's the closest? I would say probably job title. It's probably the closest to our guide here. Employment category. Yeah, job title should be the closest. So we're going to take job title, and then we're going to look, we're going to go back into our document. And we're going to move that over. And then we're going to ask it for a bar chart. Frequency percent valid. Yeah. So it should be like, let's see. Statistics. Yeah, frequency percent, valid percent. So let's go. So. Yeah, so let's just grab our dispersion. So let's check those boxes: standard deviation, variance, range, mean, median, mode, because we're all familiar with those. We'll say percentiles. No, not percentiles, because that makes it wonky. So just these, just central tendency and dispersions, we're really familiar with those. Click on continue. And then we're going to click on charts, bar chart, continue, okay. And then it's going to tell you the frequency. So what these are the frequencies of how often people that are in that particular job. It's basically counting the number of times the thing happens. This will tell you the percentage and the cumulative percentage of people. And then as you can see, it's going to get all the way up to 100%. And then if you've done the bar chart and you scroll down, it's going to give you a breakdown of the frequency and the job title. Same thing over here for everybody watching on Zoom. Analyze script statistics frequencies. We're going to grab job title, move it over. We're going to go statistics. We're just going to check the stuff we're familiar with: central tendency, mean, median, mode, standard deviation, variance, range, standard error, minimum, maximum, continue, charts, bar chart, continue, okay. And I believe that is, yeah, that's it. And we're gonna stop across tabulation. So then you're gonna want to save it as a SPV file. Now, if you have an SPV file with both of the things you did for 1 and 2, I'll accept that. All on one, that's okay. But now your SAV file should be 2 separate files, because if you've imported it would like mess it up. So if you did new data and then you imported, you should be fine from Excel. But if you have 2 output, if you have 1 output file for everything we've done, that's okay. Save it. And now we're going into chapter 7 by hand. That's all we're doing with SPS, is just getting your feet wet, knowing where to click. Because if anyone wants to see what we did again, we can do that. We're just doing central tendency, standard error of the mean, variance, range, and then a bar chart. And before we did descriptive statistics and asked it to spit the same things out with the gross income, which is very similar to it. When you get the cross tabulation for the guide, you're stopping. So we're just getting a sense of more getting our feet with SPSS. And standard error of the mean, yeah. So all you have to do is just download the Excel file and then go file, new data, like not here. So all you do is you go right into like, you just go, you can go file, and then you go new data. Just so like you have a brand new one of these. And then file, import data, grab Excel. And then find your file, click open. And then okay. And then you're just gonna go analyze. Follow me so far?
I'm saying, like, do you want us to include, just like save this?
Save this, so I know you've been able to successfully import from Excel.
Oh, okay. How was the other one? Because I already exited that. How was that one? Thanks.
So just re-enter it. I mean, because it's like 10 numbers.
Okay.
Like if you go back to the worksheet 272, just relabel them, enter them. And then if you already have your output file, I'm checking to make sure you guys know how to do both sides of SPSS. Make sense? Or do you want me to come over and walk you through?
I don't know, I just need to do it.
Okay, all right, no problem. So we're just doing like a couple steps and then we're done. That's it. Yeah. That's it. We're done. And you can say submit the worksheet. Like that's it. And then chapter 7 is some probability stuff, which is very straightforward. And then we'll jump into 8 if we have time, or we'll do it next time. And at this point, like you guys did the chapter 7 post test and the WebAssign in the near future, probably by like early in the week next week.
Yeah, I uploaded it to, I sent it to my Outlook today, but on my Outlook.
If you decide to send a JPEG in that I can read, I'll allow that. If you want to scan it, I want to know it's an SPSS though. Like I want to be able to see, that's why I was saying, just if you save it as SPV or SAV, I can just open it on my computer. What was that? Sure, yeah. Yeah, SPV, that's your output file. Yeah, yeah, that's perfect. It's wherever you download it to, so it's probably in like a different download folder. Just check like, what the problem is like the path. Yeah, yeah, that was that one, and then the other one, yeah, that's it, yeah. It's just a couple outlets, it's. Yeah, something like. That's fine, yeah. That's fine, as long as it's the right extension. What we don't want to do is we don't want to do .sav, .spv, like 2 file extensions will confuse the heck out of it. Just make sure that they make sense. So the reason you can't see that your desktop, it has to do with the path. So save as, it's in documents, change that folder, find downloads or desktop, yeah, just so you can find it, resave it. It shouldn't give you that pop-up, and now if you try to find the file, it should be on your desktop. Yep, there you go. Perfect. Yes. The SCM 17, 20, and 23, because 20 was our mean. Then number 6 was the standard deviation, which was 20, and then it was 6 to the right, and one that I erased them. Though the number in the middle was, it was still 20, and then it was 6 standard deviations, so it would have been 26 and like 14. And I drew that earlier, but I think I erased it. Make sense, everybody? Yeah, that'd be awesome. Yes, you want to take a look? What the numbers again? Oh, sure, I can put that up there for you. You're talking about should be window. Where is it? Window. I think I closed out of that, but that's right here. It's right here, statistical. Those are the numbers right there. 93, 66, 30. I can zoom in if you want. Can you see that okay? Okay. SPV output, SAV data. If you want to be fancy and you want to click on save as export, you should have some Excel and or PDF options in the export option. I believe it's a PDF option for SPV and it's a Excel or CSV, comma separated value or comma delimited value basically for Excel. I'm saying just save it in SPSS because it's simpler. There are absolutely jobs out there that say must have SPS experience and not necessarily teaching. Like there are analyst stuff for your industry and stuff. This is a specialized skill set. Now, if they don't have, you only have one license and they don't have that, you can export to a PDF file and like show them something they couldn't read it. By the way, just so you know, anybody a fan of open source?
What is that?
Open source means anybody can use it. You don't have to pay for it. So I'm going to teach to SPSS. I'm not going to teach the open source, but I want you to know there is an open source out there. It's called Jamovi. Where I'm not going to teach you to Jamovi, but Jamovi will import and export Excel, SPSS, etc. So you can have an SPSS file, work with it in Jamovi and export it into an SPSS file and hand it in that way. So if you needed a basically free and not a license, use Jamovi. Jamovi is very compatible with SPSS. I'm not going to teach you guys Jamovi. It's all open source. You can read about it on your own if you wanted to. Most of companies out there want SPSS skill set and the curriculum at 2 pages designed for SPSS. So I'm not going to teach you Jamovi. I'm just saying you want open source in the future, you could use this. There's a free like manual that shows you how to use it and everything. And there's also like packages you can download to have more stats options. So just if you're ever like a couple of years from now, you're trying to do some data and they want an SPSS, or you're trying to freelance or something comes up and you can't afford the $1,500 a year for the SPSS license, Jamovi's free and you can move stuff in and out of SPSS that way. You can use Jamovi to do the same stuff that we're doing. And you can convert the files back and forth to Excel, to SPSS. Even if you don't have SPS, what you can't do is you can't open SPSS and look at the file, obviously. Like I said, I teach a grad stats course and I tell them SPSS or Jamovi because I'm creating the curriculum from scratch. And I say you can do either per due page, but I think I think this is the future, but SPSS, a lot of companies know it and they don't know about Jamovi. So the skill set you have that you're going to take with you into the real world, because you might use stats, you never know, would be SPSS. I'm just saying, here's your free version if you wanted or needed to use it. So let's jump into the other worksheet when you guys are ready, or a break, and then we'll jump into 8. You want to see column C for the unit normal table? Oh, I gotcha. You mean like the answers? Oh, I gotcha. Sure. That's no problem. That is right here. Student. Instructor. This column C. Can you see that okay? Should I zoom in? So I believe it's just the second half. If it was B and C, it'd be those other worksheet. Because it was all these. So column A, it was column B and C. then it was Z-scores, and then it was Z-score. So you should have answers like this for all 15 of those for that previous worksheet. And then the first half should be like roughly 7 through 15. Because I said go find the Z-scores based on those. And if you email me, I don't have a problem posting these in the announcements. Because with the answers, like, yeah, I know how you got there. So if you're checking the answers to figure that out, so you know what to do in a test, that's fine. So if you want, I could post this, or you can take a few minutes to look at it or spot check. Okay. So the next thing we're going to do would be the other exercise, chapter 7 review. So I don't think you guys can see that yet. How's everybody doing? We're about an hour out. Do you want to take a short break, or do you want to take a break after the worksheet? I can do at least one more break before the end of the day. You guys want to take a short break? Let's call it 5. And then if we can build one more break in, we will, but we'll do at least 5. We'll do 5 right now, which is another Fibonacci number, by the way. If you guys are bored and you're interested, check this out sometime.
Really admitting his feelings.
Just for fun, not that I'm going to teach. I'm just saying, if you're just interested, check out Fibonacci numbers. They're everywhere. Yeah. It's what it is you take this number 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. You see how I'm getting there? 2 plus 1, 3, 3 plus 5, 8, 8 plus 5, 13, 13 plus 8, 21. There's also retracement ratios, which actually can predict predictive analytics of the stock market, the foreign exchange market, crypto market. There's actually patterns with Fibonacci where basically, those the retracements aren't the same as these are like 31, 61.8%, etc. Where basically, if you have like your graph and you have your retracement ratios, it'll go to like just this one, it'll bounce off of it. But if it breaks through the Fibonacci line, then that's your opportunity for money based on math. And Fibonacci numbers are like human DNA. They're like the sneeze work plant, where like the plant will like it'll grow 1 leaf, and it'll grow 2 leaves over here, and then 3 and 4. So it's fascinating. Phil's Fibonacci like a couple hundred years ago. Figure that out. Yeah, it's like, but it's not really like stats, but it's just interesting. They're everywhere.
What were you saying? Like,
Yeah, it's in human DNA. And it's in human DNA, and then quite ironically, religiously, I don't know what we don't do that respect that you don't. It did happen with Christ, because 1, 2, 3, 4, 5, 6, 7. That's the 7th Fibonacci number. 12 disciples, 1 leader. Interesting. Just math. Whatever you do, just
the main one, the DNA.
the DNA is interesting too. DNA, and then the plant, this plant that it shows it with is, I think it's sneeze wort, I think is how it's spelled. Wort, I think. Does that pattern? But Fibonacci numbers are super interesting. I'm just gonna the restroom real quick.
Oh my God, I saw it. I was like, I knew it. Who died? TV show. TV show. Oh my God. No. I know she was like, oh my God. I love the show. Really sweet. She was like,
Oh my God, as soon as I saw that, I really like smacked my face. I was like, oh my God. I was like, it's happening. But I don't,
like,
yeah,
to go to her.
that might just be no problem because I hate.
His character was a little.
Student resources. In-class activities. We're gonna do folder B. We're gonna make this available so you can see that. Okay. Stop the screen share. Student resources.
Well, then I guess.
We're gonna go into 629, folder B. And we're gonna look for chapter 7 review. And that's what you're gonna pull up. And then we're gonna do a couple examples. And then I'll make chapter 7 pretty clear.
You said chapter 6, right?
Chapter 7 review. And let's go like this. Share. Chapter 7. Okay, so everybody ready? Think recording, so it's fine if. So first, this is just some review. Did everybody find this worksheet okay? So first, sampling distribution, we talked about this earlier. Is the distribution of all sample means or sample variances that can be obtained in a given size of the same population. Like how the sample is distributed. Sampling without replacement means you pluck something out and you don't replace it, like. Sampling. So if I'm going to sample without replacement, take a card. I'm not putting it back in the deck, sample without replacement, or with replacement. I take the card, put it back in the deck, then I grab another card. That's like your nuance and your difference. So let's find the probability of selecting a triangle marked B on the first row of 10 other triangles with a total of 2 triangles marked B and the rest are marked C. So it would be 2 out of 10 or 0.20 for the probability. Or a 20% chance if we move the decimal over 2 points by multiplying by 100. Because there's 2 out of 10. Second draw, we don't replace the triangle. So it's going to be 1 out of 9 or an 11% chance because we no longer have 10. We're doing 1 out of a smaller thing. Remember, that's always going to be the frequency The probability is equal to the frequency of the thing happening over the sample space. The sample space changed. We didn't replace the card. That's why it's 1 out of 9. Now calculate on your own the following without replacement. What is the probability of selecting a circle marked D with 3 circles marked D out of a total number of 15 circles with the remaining circles marked E? Please show your work. And then if you did not replace the first circle, you just selected mark D and you want to select another circle mark D, what is the new probability? So 1 and 2, take a few minutes to do those on your own based on the example I just showed you. And then we'll walk through it as a group. If you feel super lost, we'll walk through it as a group now, but it's literally using the same, a very similar example. What was that? This is chapter 7, review statistics. And this is under the folder 629, folder B. And then we're just doing 1 and 2. And we're going to basically create the numerator denominator, just like we did in this in the example. And I'll show you how to do that in a moment, but I'll give you a few minutes to try that on your own. Or maybe look up as you're working through that. Or the frequency of the value over the total. So does everyone, you're still working, right? Nick? So that would be 3, right? Out of 15. Got 15 cards, 3 out of 15. And then whatever your decimal point is, does anyone have that, what that is? What'd you get? Point, so you got 0.20 or 20%. Or 20%, yep. So 0.20 or 20%. And that was for the first one, the 3 out of 15. So then the next fraction would be, if you don't replace them, so we have 14, right? Because we have 1 missing. What is the new probability? Well, we already selected 1, so it's going to be 2 out of 14. So 2 out of 14, and then what'd you get for the percentage? 0.14, is that what you got? Or 14%. Now, does that make sense? Well, if we have a larger amount in our numerator and a larger amount in our denominator, the percentages would go up. We have a lower amount, it's going to decrease that percentage. 14.5 for 14%. The percent I got, of course, by moving the decimal over 2 places or multiplying by 100. Make sense so far, everybody? Okay. Some more definitions. A sample design is a specific plan or protocol for how you're going to do it. In theoretical sampling, each individual is selected and replaced. So I replace the cards in theoretical sampling. I don't in the other one. So in experimental sampling, the order of selecting individuals does not matter, and each individual is not selected is selected before being replaced again. So a researcher selected a sample of sizes 4, n equals 4 from population of n equals 11. Using this example, how many possible samples of 4 can be selected using experimental sampling? So it's page 215 in the paper book. It's probably a few pages later in the electronic text. It's under section 7.2. If you want to just see that formula, n divided by n minus n minus. So what is that? 11 exclamation point. Now I got that from n be like our population, our total. Okay. To make things easier, we could probably go like this for you. And then 4 exclamation point, that was the sample size, n, the small n, exclamation point, and then the overall, through large N, 11 minus 4. So that's going to be the breakdown of 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So the numerator should make sense. You just multiply it 11 times every number below it, all the way down to 1. And then the denominator, 4 times 3 times 2 times 1. That's this, the 4 exclamation point. And then I'm going to multiply it times 7, because 11 minus 4 is 7 inside the brackets. 7 times 5, 6 times 5 times 4 times 3 times 2 times 1. This equals 330, which is the total number of samples possible. So so this part right here is just go home. This and this are the same, right? And then your 11 minus 4, you want to do that before you do the exclamation point in terms of like your order of operations. But that is literally telling us to start with the 7. And then because it's between the exclamation point and there's really like no addition or subtraction, it's implied that we're going to have this right here. Let's make that maybe like 7. And that's basically like just in between those. It doesn't matter. You just want to make sure you're doing the probability correctly. So now I'm asking you on your own, use n is equal to 2. That's your small n, your sample size, like the number of people in the sample from a population of 9. And then create, so I'm asking you to do 2 things. Take the one I gave you and then create your own. Now you can use the steps and the formulas to walk yourself through it. And then I'll come around and or do it as a class in a second here if it doesn't make sense, but give it a shot on your own. And you can usually literally use the sample above to plug all the stuff in. Or we can do it as a class if you're really feeling lost, or I'll show you in a few minutes. So obviously, Carlos, that card trick would be 52 times, and then it'd be 52 times, and then it's 1. It'd be 52 minus 1, which would be, this is one possibility. And then you multiply that all the way out. And that was the odds of getting that card right that I showed you guys. It'd be a pretty big number. If you guys figure it out, I'll be proud of you. But I don't want to not drop the mic. I don't want to show you all how to do it. I want you to like figure that out on your own. If you figure it out, or if I do it again for another reason and you figure it out, then that would be awesome. But what I was doing is I'm manipulating the probability by counting it's based on math. Yep, based on what I gave you. Oh yeah, then when you do your own, then you're gonna create your own, but you can use like the model. Just don't use any of the same numbers that you've already been looking at. Oh yeah, that's actually quite fun. So you can impress your friends with crimes of humanity if you play that card, that game, and be like, here's the outcomes if you wanted to. So for the first one, it would be, so n is 9, because that's population size. So 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And then n, which was 2, so we would put that there, minus n, the minus n exclamation point. So 2 times 1, that would make sense. And then n minus m would be 9 minus 2. So then it'd be 2 times 7 times 1 times 7 times 6 times for the all the way down to 1 for your denominator. And then when, I haven't done the math yet, but whatever that number equals would be your number of probabilities. And then it would be however you created your own there. Does that make sense so far, everybody? How to plug that into the formula for the outcomes? Makes sense? Okay. And then you just create your own, like I said, just don't use the same numbers, and then you plug that in again. Are you guys ready to do something else, or do you need a few more minutes to do some more math or create your own? A few minutes, okay. Check back with you in like 3 to 5, give you a little time to do that. to be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by, plugging that formula in again. And then that would be 2 times 1 times 7 times 6 times 5 times 4 times 3 times 2 times 1. This was because the n was 2, so we plugged it in. 2 would be 2 right here. So if I were to take that, how we got to those numbers would have been, this becomes 9 right here. That is 9. And this could be 2. And this would be 9 minus 2. And that's how we got there. If we put that formula in. So that should be picking up my voice. Should be good to go. A few more minutes. Still working on your own, yeah? Right, come around. Yeah. Well, actually, it's 9. Three versus a researcher, 2 samples. Yeah, so now you're all, so your first number, if you look at the formula, would be. Scroll back up. Yeah, there you go. It's right there. So highlight that. You see that right there, that as we want to, so it's n divided by, so you're going to plug those numbers in. So the population I gave you is 9. So it's 9 exclamation point, which is 9 times 8 times 7 times 6 times 4. And then for your yep. And then your denominator is n exclamation. Which is 2, right? So I said the sample size. Yeah, so you see that right there? So you're plugging this number in, so it's 2 exclamation point, which should be 2 times 1. Does that make sense? Because you're just gonna go down to 1. So it's 2 times 1, and then however you want to write it, 2 times 1. And then times, now we got to do this, n minus n. So you have your capital N. No, just have one, and then you're multiplied by. So in the parentheses, no, just, I think you got it. No, you don't need that extra times 1. So it'd be 2 times 1. You see the word? So I said 2 times 1 times 9 minus 2. That was that n minus 2, which is 7. So 2 times 1 times 7 times 6 times 5 times 4 times 8 times 2 times 1. That's your denominator. And then what you'll do is you're going to get your total, your numerator, by multiplying those out. So you're dividing by your total of your denominator, and that's going to be your number of possibilities. Which you can do at a scientific calculator or a regular calculator. So. Yeah. Does that make sense? Maybe because you're like quiet. So that would, what that is. That's up here. So you take your total population and you multiply all the way down to 1. Then we're taking a selected sample size of 2. So we're saying if we get, how many samples of 2 can we get with the total population? So we take the sample size, multiply it down to 1, and then we take times your population minus the sample size, and that difference, and multiply that down. So that's 9 minus 2 right here. This is this right. So this right here is literally this. And then this right here is literally this, which translates to that. Does that help?
Yeah, I think so. That's 20.
That might make sense because you're saying the probability of grabbing two, how many different times within, like it's the outcome and the probability of like what you could get. The bigger the number are it's going to be huge. Like I was telling Carlos, the card trick would be 52 times all the way down to 1 divided by, because I only have one possibility, 1 times 1 minus 1. That would be, is that right? Like the chances of me getting that right is actually pretty low. That would be like basically be, right, is that right? No, it'd be 52 minus 1. So it'd be that, and then it'd be basically like 50 times all the way down. That would be, and then the numerator divided by the denominator would be the number of possible cards that I could flip over out of the 52. What was your question, Carlos? If you've done the math, I don't know off the top of my head, but if you've multiplied them all out, that should be right. That's probably, that's a really big number. Like almost 6 numbers. That probably makes sense. Yeah, I think that's right. Now create your own. Skip that. We did it before. No, yeah, now create your own. So all you have to do is like just take the scenario and create your own. So you're gonna say that research the sample size of n equals 5 for a population of size of 15. Just switch the numbers around and do the math. That's it. Okay, so now, are you guys ready to do the next thing? Okay, cool. Over here, feeling pretty good-ish or so? Yes, no? Okay. All right, so just some stuff, and this is actually pretty straightforward. Unbiased estimator, remember that's a sample statistic. We divide the sum of the squares divided by n minus 1. We did that earlier. Central limit theorem explains how they are from the sample, how the distribution of the scores work in terms of being selected at random will approach a normal distribution. Basically, the central limit theorem says that if we grab numbers randomly, it's going to shape it like a normal curve. That's what that theorem says. It's like an assumption of truth. The sample mean is an unbiased estimator of the value of the population mean. And the central limit theorem explains that the shape tends towards a normal distribution, regardless of the distribution of the population. So it tends to be a normal one, which is review from earlier today. In behavioral research, we often measure a sample mean to estimate the value of the population mean. And then, of course, to determine how well it estimates it, we need to identify a population of interest and then determine the distribution sample means for all possible samples of a given size to be selected from that population. So a sampling distribution. We use theoretical sampling to learn about the characteristics of the mean. We will use the sampling strategy to select samples in the population. We can use this to see how well the sample mean estimates the value of the population. So to construct a sampling distribution, let us identify a hypothetical population of people, n is equal to 5. We took the Ocean personality test. Anybody who was in Gen Psych probably took that. And assume they have the following quantitative scores. A scored 12, B scored 20, person C scored 7, person D scored 8, person E scored 9. We know all 5 scores. We're going to identify the mean, and then we can construct a sampling distribution of what we calculated. So we're looking at the formula on page 216 or 7.3. And this is literally the same thing. The sum of all of them divided by the total. Our population mean would be 11.2. We took 12 plus 20 plus 7 plus 8 plus 9 divided by 5. So we would do the same thing with these scores and then create your own. And then I just have a recap on the central limit theorem. Probability of obtaining a sample for the empirical ruling on 95% or with institute standard deviations. That was what I was drawing before. You have a bell curve. It's 95%, I think 99.7, which is within 3, and 95% within 2 standard deviations, just in terms of how the bell curve is shaped and how the scores fall. So the last thing I'm literally asking you to do is literally take these, sum them, divide them by your n. That's your review, your sum of your x over n, and get your population mean. And that's the end of chapter 7. I'll give you a few minutes to work through that, and I can certainly come around and check your math. And then I'm asking you basically to like use the same scenario and create your own, just to get practice with calculating that population mean again.
Yeah, I'm just putting it on.
Then you just create your own. You have added all the scores together. And you divided that into 6. Perfect. Yeah, so it's showing you where I was. What's making sense to you? Right on, like this. Yes. So you would do around. You would round up or down based on what you're looking at. But like, if you're talking about like practical example, you're not gonna have half the fish, so it makes sense actually to round down. Right, you're not gonna have a third of the fish, you're gonna have. What the rule is, if it's it's 5 or higher, you go up, and if it's 4 or lower, you usually go down, but it's gonna make more sense. If your scenario says like, I can't, you don't have, like, you can't have 2 points for tribes. You know what I mean, like, so if you're like trying to like, say a scenario, that's usually how you do the rounding. So you're either gonna, depending on how you're interpreting, you're gonna likely catch 1 less fish or 1 more, based on probably what your average is. Change all the numbers and create your own, and then from the stairs, you want to use the or you just like always like what? No, I would change all your numbers.
Yeah.
You know, make those scores different if you're gonna do that, or create your own, but have like, you know, few scores. So if you're low, good native fish, like you're all out fish. Based on the average fish. But 20 is right. And then you just practice punching them. So the next year, that last thing is just like this. Literally we're halfway. Are the stats making sense when we get the right answers?
Yeah.
I'm sorry, was it? Yeah, that's the main. I heard her. You gotta immerse yourself in it.
So everybody ready for a little on chapter 8? Or are you still working? Need 2 more minutes? Yeah. Yeah, absolutely.
You guys are done or so? Yeah. Okay. Yeah, the last part of it is review that like, and then in a couple minutes, they just kind of a blue center to here. Then we'll walk through some or all of 8 and we'll get through. And I'm just, now we could jump into a worksheet, but I'm assuming that the PowerPoint's more about concept and an example or 2, that we actually do the worksheet. The idea is like repetition, sort of like cleverly behavioral learning. Here's what it is. Here's an example. Here's one list of stuff you work through, then you create your own. So you're really doing like all the stuff, like what taxonomy stuff. Which if you're gonna be a professor, you want to do taxonomy. Yeah, Yeah, we didn't do that. Only lecture you guys. SPSS. Statistical guidance for the social sciences, there's like SPSS, there's Python, there's R, there's SAS. SPSS is super common. And a lot of the stuff there wants, a lot of, if you were to work on. I don't know, like. Yeah, that's what we want. It's going to like school. We meet 8 hours every week except for like a holiday, and we meet for 8 weeks or 48 minus 1 and 44. I have 320 hours on mine besides teaching. They say if you like what experience you just have class or your experience. Like I'm familiar with or
I just like to see.
or maybe like practical experience of something like practical experience of SPSS analysis or something like that, or data, or something like that if you were to use it on your resume, outside of like. Are you guys good in the back? You stay if you want. Okay, let's jump into chapter 8, front row. You're in a pretty good spot, I think, overall. Okay. Same question for you. The PowerPoints plus the worksheets are helpful.
Yeah.
Okay, okay. Because I feel like it's like you're in the cloud on the PowerPoint, and then you're like, it's actually making sense once we actually do the worksheets. So today, at best, I think I'm going to assign through chapter 8 pretest. I might say WebAssign, but we're still going to spend probably at least one more day on chapter 8, realistically. So you don't have to know this start to finish today. All right, so everybody got that? So we have hypothesis testing, significance, effect size, and power. And then we're going to walk through what that means, different types of error, what those mean. That has to do with rejecting or accepting a null or alternative hypothesis. Does anyone remember what a null and alternative hypothesis is? The difference? Hypothesis is like a guess or assumption of truth, right? A null hypothesis is that there is no relationship. So if I want to just make something up, because you see I'm drinking coffee this morning, I could say there is not a relationship with my ability to teach statistics and coffee. That's a null hypothesis. If I was saying an alternative hypothesis, I would say there is a greater than or equal to relationship with my ability to teach statistics based on if I have my cup of coffee or not. Maybe there's more neurons firing when I have coffee, maybe not. That would be the difference between those two. So we'll talk about a one sample Z-test. Like I said, we probably won't get through all of this today. It'll probably just be like some of this. Effect size, Cohen's D, factors that power and factors that influence power, and then how to summarize APA results. So why do we want to do this? We want to see if something we can assume is correct. We want to see if, for example, let's say students, and this is coming up in our worksheets, they have one language at home and another language, say in the classroom, like maybe they've immigrated to America for whatever reason, and they get immersion with teachers in their secondary language, and we try to see if that's helpful with their learning outcome. That might be something we can do for a hypothesis. We might say something like students reading out loud
in the presence or not in the presence of a teacher. Again, an example coming up, whether or not the hypothesis is true. So purpose test claims or ideas, goal, the likelihood, and then we're going to deal with the mean to figure that out. And there's 4 steps to hypothesis testing, which we're going to do all 4 steps in our worksheets. So there will be practical examples. So like I said, if it doesn't make sense right away, it's okay. Make sure everybody has that. So we're going to have the alpha level that affects the probability of rejecting the null hypothesis. Your alpha level is written like that. It's tied to your power level. So the power level, we're trying to deal with like greater than probability. If I want to think of like an object or something, and I want to see if like you're able to telepathically read my mind, we need something better than like 25%. We need something better than like chance, like better than 1 in 4. We talk about power. The accepted amount is 0.8 for the social sciences or higher, with an 80% or higher likelihood of something, or a power 0.95% or 95% likely that we can make the assumption of truth. So your alpha would be 0.5. The alpha plus the power equals 100%. That's how you get your alpha level is against your power. 0.8 is the power level acceptable for the social sciences. With 80% accuracy, we're making an assumption of truth, your power. 95% is usually what we're going to do in this class. That's better. I can say with 95% accuracy. It's the minimum. It's the minimum. 95 is way better. That's what I would encourage you to use. 80% is the minimum exception. Like what we're going to accept. So let's just say children, statement about the parameter. Children in the US watch an average of 3 hours of TV per week. And null hypothesis, statement that contradicts it. So null is just like nothing's really happening. That's like your starting point. Alternative is more or less. So example, children in the United States watch more or less than 3 hours of TV per week. 2 tails are outcomes, left or right of that mean, their bell curve. We're trying to see, is it more, is it less? Null is sort of like that. No relationship, or like basically like a starting point. Alternative is we're trying to see if there's like a relationship. So we're going to predict H1 is how you write alternative hypothesis, or you write HO for null hypothesis to be greater than, less than, or not equal to the null hypothesis, whereas a null hypothesis would be like nothing happening, or it's equal to, like, which is basically like no relationship. It's equal, like what's it doing? Nothing, right? Makes sense? Then we're going to set the critical level. Don't worry, we're going to walk through this and let that freak you out. We're going to look at the critical level. What is calculated greater than error by chance? Default level, 5%, that's our alpha. Probability of obtaining the statistic measured in the sample, if the null hypothesis is true. And the probability of obtaining the sample mean is less than 5%. If greater, we reject the null. The critical level so we have a critical level right here. This will say we'll call this your critical level. Don't worry about a number at this point, but we're basically saying the bell curve. If you're at or greater, that is going to be retain, alternative hypothesis, or reject the null. And if you're in here, it's the opposite. It would be retain null and reject alternative. So at or more, this is never, if it's right on the line, it's that direction. When I first was immersing myself in stats, I looked this up, it's at or more. Compute, everybody have that so far? So that's just a critical level. We're gonna do very specific examples that explain what that looks like. And then we're gonna use our unit normal table to tell us where that critical value is. Then we're gonna plug that value in to see if something happens or not. And then we're gonna determine if we retain or reject the null hypothesis and vice versa. If we retain one, we reject the other and vice versa. And then it's in terms of where it is into the curve. Yes. So it's before wherever the critical value is. And then the critical value is anything beyond as the tail like goes on sort of like forever. And then if we're dealing with two-tailed, we're talking about this and this for two-tailed, and we're talking about one tail that's that one or that one. Yeah, less than, more than. So we're gonna look at so critical value or greater, I mean, or less than, or this way. That's your alternative. Null is everything that's sort of like left over. We're trying to see where the critical, like where the breakoff point is, like where it does the thing. It'll make sense when we start to get into the worksheets. So let's see. Helps determine how likely it is. When I'm talking about likelihood, I'm talking about the power or that alpha level. With a 95% accuracy, I think this thing's going to happen. Because I have an alpha level of 0.05. Larger value, the test statistic further sample mean deviates from the population mean state in the null hypothesis. Sort of have that, but natural. Where are we? Here? Here? Oh, backwards. What are you asking me? Step to this? No, if the null hypothesis is true. Under the curve. Before you have that breakout critical value. Null is a starting point or like something as equal to, greater than, less than, alternative. So now we want to make the decision. We're going to walk through these steps in the worksheets. Okay, so this is just like the concept. We're going to look for the p-value, the probability value. We're going to use that unit normal table to find that. We're going to use the power and the alpha level to drive what we're looking up. I'm going to walk you through how to do that. You reject the null hypothesis. If you reject the null hypothesis, the alternative is correct. The sample mean associated with low probability of occurrence if the null is true. If your probability value is less than 0.5, you reach significance and you're going to reject it. You're going to retain it if the sample mean associated with the high probability of occurrence when the null is true, probability value is greater than 0.5, failed to reach significance. We're going to walk through examples. This is just a sense of what you're looking for at this point. And we're going to walk through examples like Monday, because we will run out of time probably today. Today, I'm going to give you as much structure as I can, kind of till time here. Does everyone have that? You still take your time, everybody. It's absolutely fine. So what we're trying to figure out is a probability of getting to the sample mean in terms of the change. So of what we're trying to look at. So leave that up until you're. So we need to know the population mean, which we know how to calculate. And we need to know the standard error of the mean, which we just walked through today. You need to know those two things to work on your sampling distribution. So your mean or your sampling distribution. There's our formulas for your population, your standard error of the mean, which is always, if we're talking about, you have your variance or your standard deviation. Ultimately, we're driving towards that standard error, which is that last formula right there. Standard deviation divided by the square root of the sample. So you could literally have raw data and get those numbers. Make sense? So once, no, I think you're still checking, copying and writing formulas. Is everybody good? Still copying stuff down? So making a decision, step 4 is you decide what you're going to do. Are you going to retain or reject the null? Type 2 or B error, I'll show you what the errors look like. Decision to reject the null, correct. Decision to reject the null. So if you make the wrong choice, that's where you get a type 1 or type 2 error. So if the decision to retain, you could have a decision to retain the null, which would be correct, or you could have the decision to retain the null being incorrect. That'd be your type 2 error. And then you have decision to reject the null, correct, or the decision to reject the null incorrect, which is a type 1 error. And we'll walk through like how you can get into those. Truth in the population. You can either correctly reject or retain the null hypothesis, or wrong, incorrectly reject or retain the null hypothesis. This has to do with your decision and if you're getting it right, and the type of errors that you would make in terms of what you did incorrectly. Those are 4 different outcomes. So you would use as if like you do the math and something like seems a little bit off, you probably got a type 1 or type 2 error, which is probably one of these. You either retained it, you either didn't, you shouldn't have retained the null hypothesis, or you shouldn't have rejected the null hypothesis, depending on what is true.
So the output is type 1.
It is. Reject the null. Yeah, reject. Yeah, that's
Like when you did the 0.05,
mhm.
that's the
The 0.05 is the alpha level, which is tied to the power to get us to 1. The error is more if we did it incorrectly, but it's all tied together. I have that so far. I'm going to walk through like how we get to the errors in a second, Katie. So I think it'll make more sense. It usually has to do with like the tails. So like maybe you didn't think through it correctly, so you can always go backwards. So for example, type of 1 error, you decided to type 3 errors. Type 1 error for one-tailed tests. You decided to retain the null hypothesis because rejection region was located in the wrong tail. If I'm going to reject or retain the null, well, we did the wrong tail. It was greater than, less than. We didn't think about it correctly. That's type 3 error, retain null hypothesis, wrong, rejection region, wrong tail. So you want to make sure you're correcting the right, you're looking at the right tail. We're going to do 1-tailed and 2-tailed tests in the worksheet. So I'm going to give you scenarios on how to walk through that so you know how to pick the right one. So we're trying to figure out the probability of our null hypothesis or alternative hypothesis being correct, and with what confidence we can assume that we're right, which drives our power level and our alpha level. Does everyone have that? Do I need to go back? Anybody? Colleen, you sure you're all right? Okay. So alpha level is the level of significance for the hypothesis test. Type 1 error by stating level of significance, alpha level. Significance level, large probability of committing the type 1 error. You can allow us to decide to reject the null hypothesis. Default is 0.5. That is compared to the p-value in making a decision. So the probability value. So I'm going to say, hey, does this thing that I'm trying to do, this intervention or this treatment work? Whatever that might be. Yes.
When it says significance level, are just probability of committing an error?
Yes. Committing the type 1 error. Yeah. Because we're going to say with this amount of, like, we have that power, and you're right, 0.8 is, I think, low, 80%. I like to use a 95% probability of getting my null or alternative hypothesis right. I could still be wrong, but it's unlikely using the math behind it. Your power is the probability of rejecting the false null hypothesis, likely it'll detect assuming the effect exists. So the higher the power is, the better chance you have. If I said a 0.4 power of 40%, you'd have a larger chance of getting it wrong. The higher it is, you have a lower chance of getting it wrong. Make sense? So power plus alpha level, that gets you to 100%. And we'll be referencing the Z table.
When it says rejecting false null hypothesis, would they the true one?
Yeah, yeah, probably, yeah, rejecting the fault, yeah, so probably, so likelihood we'll be able to tell, and then we'll pick which one we're doing, retaining or rejecting null or alternative hypothesis, depending on where it is into the curve and the critical value. One sample Z-test. This is used to test hypotheses concerning the mean in the single population, known variance, non-directional, and two-tailed test. Alternative hypothesis is stated not equal to or null, and we're interested in any alternative from the null hypothesis. So a non-directional, two-tailed, both sides of the tail. I'm seeing if something happens in terms of the critical values being to the left and right, where basically the thing does happen. Like I said, if it's directly on it or beyond it, that's when it breaks away. If it's right below it, then we're below the curve. I think we'll end with directional in just a second here. Yeah, because this should really make it clear for everybody. You good? Okay. So then we have directional, one-tailed, left or right. Stated as greater than or less than. Upper tail, critical test, alternative hypothesis is greater than null hypothesis. Upper tail to the right. Lower tail to the left. Level of significance placed in the lower tail of the distribution. So we have non-directional. Is it happening here and or here? Or based on our scenario, is it less than, greater than one, left or right side of the tail? We're going to walk through some practical examples of when and how you use this, but we're going to do that next time. I would say pre-test chapters 7 and 8 No post-test on chapter 8 at this point, because we haven't finished it. I can put this in the announcements too. Chapter 7, WebAssign for sure, probably before next class. Chapter 8, WebAssign not yet, or maybe, but I'll give you more time to like work on it. No post-test on chapter 8 at this point. And then in the next class or two, we'll start doing the reviews again. Exam 2 reviews where you all do this. That'll be another hard deadline. And I believe I also have an exam 2 worksheet we can do in class before we get to the exam. And then we just have chapters 9, 10, 11, and 12. And then one more exam. We're still clipping along fine because we're in the first week of July and we only have like 4.5 chapters left. We'll address chapters 15 and 17 if we have time. Those will be extra credit for you though. Any questions, thoughts, concerns on anything at all before you guys go today? I'll say do before next class. In fact, I'll say all the homework's due before next class. And I'll post them in the announcements for you. So you have like, what, 5 days, 5-6 days to work on everything. If you have any concerns or anything about anything that we're doing, just talk to me before we get to the deadline or on the day of the deadline. Other than that, have a great one.